He's a child, baby. He doesn't know window.
Stop. Baby toys.
Instead of like an ibuprofen or something, carry toys to avoid headache. My suggestion. What? It's either that or toys. Baby next to you wouldn't know after the.
This thing works? Okay. All right. Goods, chores, and mixed.
Okay, you want to put it somewhere with your. Yeah, I will do that.
45 minutes.
I just do one quick announcement. So there's you might all the PhD students might have got a mail regarding PhD clinic. It's a program typically run by SCM to connect PhD students with faculty members. So actually we have 25 faculty who has given slots to meet students. Yeah. And so far we have only 3 students signed up. So typically we there's the other problem which happens where enough faculty members don't sign up. But yeah, it's a good time to talk to meet people. Yeah, we will schedule the meeting and give you a room. Of course, you can obviously meet anybody at lunchtime and everything. But yeah, if you want a dedicated 1 hour slot or something, we can block that. And there's enough faculty willing to spend that time. Yeah. So do reply to that form. That's all. Thanks.
Hi, good morning, everyone. Okay, so welcome to the second day of the workshop. Today's first talk will be by Ruta Mehta from UIUC, and she'll be talking about fairly allocating goods, chores, and mixed items. Yeah.
Should I switch it off?
Yeah, maybe.
Okay. Thank you everyone for coming to the first talk in the morning after a very eventful day yesterday. I thought you would be like happily exhausted. Okay, and thank you to Sujit, Umang, and Siddharth for this opportunity to talk to all of you and meet you all. Okay, so today I'm going to talk about goods mix, bad chores and mixed. And so let's see what's the setting. So, I mean, we have been, it's very natural to talk about allocating goods. And, but I would like to argue that chores are as naturally appears in our real day-to-day lives, allocation of chores as goods. So labor market is one classic example of chores allocation. So TaskRabbit is a famous app in US where you want to hire people to do tasks, whatever task it is. And I found out yesterday that there's something similar within India, probably more than one such apps for hiring people to do get things done. So general problem, we're going to talk about divisible items, not indivisible. Okay, they could be goods or chores or maybe mixed. What do I mean by mixed? An item might be good for somebody and chore for somebody else. Okay, and you want to allocate these to these agents. These agents have different valuations for these items, negative, positive, whatever. Negative if they are chores for them, positive if they are goods for them. And we want to do for fair and efficient allocation. Lots of applications. By now, you are convinced fair allocation, how important it is. So I'm not going to go deeper into it. But like school seats. So here it could be, let's say, school seats assignments or teaching duty assignments, kidney exchange, vaccine allocation among different states. Let's say you are dividing, let's say, dissolving a company and you are trying to divide assets and liabilities of the company, or maybe inheritances, or maybe defense budget among different wings of defense, or defense duties among different wings of defense, or I mean, you can think of many. That's it for a motivation. Now all technical, okay. Okay, so model, N agents, M items, divisible, each of one unit without loss of generality. Again, items can be goods or bads. Agents have valuation functions that might be different. It's a concave valuation. So, and don't think of this as a positive axis. It could be positive or negative, whatever. And yeah, but concavity is one thing we'll assume because that generally captures the decreasing marginal returns and typical assumption. And again, recall that we want to do fair and efficient allocation. So these are the inputs and you want to find fair and efficient. And now you can start asking, what do you mean by fair and efficient? We have seen quite a few definitions of these yesterday. But let me give one motivating example why sometimes we really want both of them together whenever we can, right? So let's say Alice and Bob, they have a half moon cookie, half chocolate, half vanilla. Alice is fine with both of them, 50-50, when she is indifferent between the chocolate and vanilla. Bob likes vanilla and hates chocolate, let's say. And let's say we have these three out for possible way of dividing the cookie. The red line is the dividing line. Which one do you think is fair? 3 is fair. 1 is not fair? No? Why? If the guy doesn't know girl's valuation, which could be the case, then can he complain? No. Right? Okay. How about 2? So probably each one of them seems to be fair when they only know about their own valuation because they are getting at least half of the cookie in quantity, and at least they value their portion more than the other's portion. Right? Envy freeness, we have been seeing it. All 3 are envy free. But you would definitely choose third one. Why? What's the added? It is envy free, but the other 2 are also envy free. But obviously you should choose third. Why? Welfare. Right? Efficiency. This is Pareto optimal. Bob gets everything that he likes, and Alice gets half of whatever she likes, but anyway, she has a homogeneous valuation over the cookie. Right? So that's why we want to sometimes ask both efficiency and fairness together. Definitions of both of them, you have seen envy freeness. No agent envies the other agent's valuation. Proportionality. I was taking examples here, but you have seen this so many times. I don't want to bore you again. Proportionality meaning every agent gets, if there are n agents, every agent gets 1/n fraction of her value for the entire set of items. Okay. Pareto optimality, you all know, it's if this is allocation, this is the utilities agent gets, there should not be any other allocation achieving Pareto dominating utilities, right? And then you can talk about welfare. And typically in optimization, we talk about social welfare, but that doesn't make sense here when we are soliciting valuation functions from agents, because I might be reporting my valuations in rupees, you might be reporting your valuations in dollars or pounds or whatever, right? So it has to be somehow scale invariant, and welfare is not. Some of the utilities is not, so will be after Nash welfare, which is the product of the utilities. Okay, any questions about the definitions of these notions? NV freeness, proportionality, Pareto optimality, and Nash welfare. Everybody's okay with these? Yeah, okay. And we want to achieve all of them together, and for divisible case, we are in luck, because competitive equilibrium with equal income, I'll define what this is, indeed achieve all of these for a wide range of utility functions that we care about. Okay. So what is competitive equilibrium? Now start thinking about markets. Okay, so in what you suppose what happens in market, there are buyers or agents, and there are items on sale in the market. There's some prices assigned to these items, and buyers have some money, right? So depending on how much money they have, they will buy whatever they like the best from whatever they can afford. Okay, at this point, they will not worry about how much is available. Okay, if you can go to a shop and ask for something and they can say, oh, this is not right now available, but we'll make it available tomorrow. Right, that happens all the time. So they don't care about supply constraints when they're asking for what they want. They just ask whatever they like the best among everything that they can afford from the money they have. Okay, and this defines their optimal bundle. When you aggregate everybody's optimal bundle, that defines demand for every item. Okay, and we say that these prices are at competitive equilibrium when demand equals supply. You might have seen this like demand curve, supply curve, wherever it meets, that's the equilibrium prices. Like you may have seen this in Econ 101 or some kind of course, right? So that's the basic definition of competitive equilibrium, intuitive definition of it. So at given prices, every buyer buys what they like among the affordable bundles. And when this happens, demand should be equal supply for every item. Okay, and we say that it is competitive equilibrium with equal income if everybody has the same buying power. Everybody has exactly $1 or 1 rupee to spend, let's say, or 100 rupee to spend. Okay, that's equal income. Now let's understand what are the nice fairness properties of CEEI, competitive equilibrium with equal income. So first, note that it is NV free. Why is that? Why is it NV free? The competitive equilibrium with equal income allocation has to be NV free. No agent should say that I don't like my allocation, I like somebody else's allocation. You could have just bought that. All of you have just $1 or 1 rupee to spend, right? If I like your allocation, why didn't I buy that? Right? So NV free just falls out naturally. Then using NV freeness and properties of valuation function, you can get proportionality. Okay, the fact that you are going to be allocating everything, supply equals demand, right? You get proportionality. And there's a first welfare theorem that's again not very difficult to prove, given that you're allocating everything and everybody is buying their best bundle. You can just prove proportional Pareto optimality. And finally, you can also get Eisenberg-Gill in 1954, I think, or 64, showed that it also maximizing Nash welfare for a wide range of utility functions. Okay, but the other three holds for arbitrary concave valuations. Here for this one, you have to restrict your valuations to something called homogeneous. I'll define what that is. Okay. So nice. So that's why competitive equilibrium, I mean, this is a classical notion in economics. It has been studied for now centuries, but it is also as much relevant for fair division. And so existence of equilibrium is known for very general model where agents are not coming with money, but it's in barter system. And it's actually more general than when agents come with money to buy stuff. And they could be firms. And so it's much more complex setting for which they studied markets. Of course, markets are much more complex than that, the model I showed. Right? But what we will focus on is the model that makes sense for us. No, there is a supply. I said, let's assume that it's indivisible. Very important. Everything makes sense only in divisible case. Indivisible, yeah, all bets are off because of what you just said. Yeah. Prices are evolving. So you have to fix the prices so that, but I think the question is like, if there's one copy of one item and everybody likes only that, then how are you going to do NV-free allocation? Not possible. But this is divisible. You're going to allocate 1/nth fraction of the item to everybody. And extensive work on computation. Like before, yeah, so okay, Eisenberg year was 1959. But like before computer scientists started looking into it, even economists and OR operation research people have looked into it quite carefully. They didn't quite care about polynomial time computation, but they had really pretty algorithms and convex programming formulations for computing market equilibria. But when computer scientists jumped into it, we started talking about polynomial time, strongly polynomial time, and so on. And we do have those algorithms for additive valuations that pair division community cares a lot about. But there are, if you go beyond additive, then things are hard, but there are nice, simple, simplex-like algorithms there. And in general, the problem is polynomial if the utility functions are nice and homogeneous. Otherwise, in general, they could be PPAD hard or fixed P hard. So basically, the point is that there's so much work that if I just start talking about this work, I will just consume all my 45 minutes. So this is just like, that's why all the dots. You like some of you might also have worked on this. This is not at all exhaustive, but the point to make is from this slide that it's extremely important concept for the goods has been studied extensively from various aspects. Algorithms, complexity, learning, matching mechanism, dynamics, blah, 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 blah. Okay, price of anarchy, lots of things. What about bads? Okay. I tried to convince you that bads or chores are as natural as goods. But what do we know about competitive equilibrium for bads? But now, if you ask agents to pay up for consuming bads or chores, they're not going to consume anything because bads are negative. It's pain to consume them, right? So it's going to be the payment has to be the other way around, right? The bads, the chores have to pay to the agents for them to do them, right? So the prices are actually payments now. So that's why I put a negative sign here to emphasize that these are payments. And now, again, the agents have earning requirements. They don't have a budget to spend, but they have earning requirements. And based on how much they dislike these chores and how much they have earning requirement, they're going to demand their optimal or least painful bundle subject to earning requirement. Okay, and that defines their optimal bundle, defines demand, and again, demand should be equal supply. Exactly same, there's the money flow reverses, that's it. And instead of maximizing utility, now you're trying to minimize the pain. Okay. Okay, and equal income, everybody has the same earning requirement of, let's say, $1, 1 rupee, whatever. Okay. What about mixed? This is a tricky one because an item could be goods for somebody and chores for someone. So first of all, you have to differentiate between goods and chores. Qualitatively, these are goods. Qualitatively, these are chores. And then the goods will have positive price, chores will have negative. And again, the same thing. You have to be very careful about defining CEEI here, because should there be $1 or 1 rupee of spending, or should be 1 rupee of earning required? Okay, it's instance dependent. Okay. Remember, we are finally not trying to solve market equilibrium problem. We are in the fair division problem. Okay, so there are no real budgets there, no real earning requirement there. It's a dummy thing we are introducing to finally get to a fair and efficient allocation. Yes. Yes, agents valuations. It could be different for different agents. So you take a good, so I'm going ahead of myself, but if you take a good, an item, if there is somebody who values it positively, let's just talk about additive for simplicity. If somebody values it positive, then you put it in the goods. If everybody values it negatively, then put it in the chores. Yes. You have to be very careful about whether the budget should be +1, 0, or -1. There'll be 3 cases. But let me take this at the end, okay? Because the elephant in the room is bads. Okay, and let me kind of convince you of that. So these guys, Bogomolov, Mola, Sadomarsky, and Janovsky, looked at this problem with bads and mixed both, and they focused on one homogeneous valuations. What are one homogeneous valuations? So remember, we were focusing on concave. Concave look like this pictorially. One homogeneous, on top of that, requires that value of a bundle multiplied with a constant A is exactly A times value of that bundle. Okay, if you scale up a bundle by a constant, your value just scales up by the same constant. This is called one homogeneous. And many, many utility functions that we care about or economists care about, like constant elasticity or substitution, if you don't know what that is, don't worry. But additive, we care about additive, right? Additive sits in there. Okay, so for simplicity, just think about additive all the time. Okay, so this is what, and they characterize CI completely for this case. But what they observed in that characterization was that the set of equilibria could be non-convex, even when your valuations are additive. Recall that we had Eisenberg-Gale convex program for one homogeneous valuations where all items were goods. Once you have a convex program, the solution is going to be a convex set, right? But here, even for linear additive valuations, CI set could be non-convex. It could be disconnected and could have many, many components, okay? And because of this, they write in their paper that we expect that computation might be difficult, even for BADs. Existence is still through a fixed point argument. You can have a fixed point argument, but they have another argument, which is, I will show you for one homogeneous what the argument is. Yeah. So that's how they get the characterization. But you can have a fixed point argument as well, yes. Okay. And allocations and prices, both. Disconnected. There could be exponentially many. I think that's what they should.
The space of R in the R n cross n. So the only
Allocation. Disconnect. So like you can construct a non-degenerate market. Everything is points. So I think they look at BADs. So let's say -1. And then that's my guess. And then they finally, the entire paper is for mix. So they're going to characterize, it's written in an economist or mathy way. So you have to really decipher every line. But essentially, yeah, I think that's my guess. How they came to the characterization, they extended that to mixed. Competitive equilibrium with equal income. So that constitute the prices and the allocation at competitive equilibrium when every agent has equal budget. Allocation, price comma allocation, you can also just look at competitive equilibrium, just prices only or allocation only, anything. Any 3 possibilities are disconnected non-convex plow. Additive, you can prove that there exist rational valued solution. Yes, but that's a different argument, not their characterization. So using that fact that you asked, solutions are rational, the way we prove it essentially help us give a polynomial time algorithm where number of agents or number of items is a constant. This was work by Brenzai, Sadomersky, and then it was followed up. It was for BADS, and then Jugal and his student Peter proved it for mixed. And I think these guys had it for number of constant number of items. They extended to constant number of agents and to mixed. Okay, so then the question was, what's the complexity of the problem when we remove these assumptions? Okay, we looked at this, then we said, okay, we don't even have an approximation algorithm. So how about just, let's start with approximation. Okay. And what we show is that so first we get an algorithm for additive valuations, which is a different method. It's an exterior point method that I'll talk about. We extend it to one homogeneous valuations and also to mixed mana under some conditions. So main thing I want to convey is this algorithm because it's a technique, it's a new technique as far as I know, and might be applicable to other problems, okay? Non-convex optimization problems. Then we looked at exchange model, and the problem turned out to be immediately intractable, even for additive valuations, and only BADS, the problem is PPAD hard. And note that in contrast, the goods case is polynomial time solvable. Okay, strongly polynomial by now. And for separable concave valuation, of course, this is hard even in goods case, so it's hard in BADS and mixed. But we can prove that there exists a rational solution, odd number of equilibria, and containment in PPAD through like the simplex-like algorithm thing, the Lamke-Hausen algorithm. Okay, if you don't care about all of these things, what I'm going to talk about today is this exterior point method. And then if I have time, which I don't think I'll have, I'll just give you a brief overview of this particular result. Okay, so let's start. Before that, any questions about the results, the setting, the difficulty of the problem?
The mixed setting was really efficiency. Is there some analog of mass welfare?
So there is analog of Nash social welfare. Yeah, you have to be careful because it's a positive negative thing. That's why I said that. So what, as soon as you get an instance of mixed, let's focus on additive, you're going to categorize it as a goods instance, a neutral instance, or a BADS instance. So it's either a goods heavy instance or a neutral instance or a BADS heavy instance. Accordingly, you will define. So Nash welfare is a tricky one with negative values because you would want to minimize the product, right? But okay, I'm going there actually. Yeah, so okay, let me just hold on for a minute and we are just going there, okay? Okay, so again, recall the setting. You have n agents, each has earning requirement of $1 rupee. You have m divisible chores. Okay, I'm going to focus on BADS because mixed is too complex. So let's just, to understand the basics and the most important ideas, let's just focus on BADS. And the supply is without loss of generality to assume that the supply of every chore is 1. And agents have additive valuation functions, okay? So Vij here, remember, it's a pain. So if you consume 1 unit, you get Vij value, but this value is a negative value, okay? So it's very difficult to keep track of the signs. So I'm going to convert it to a disutility value, which is always positive. But now I'll think about, instead of maximizing the value, minimizing the disutility. Okay? And again, recall that competitively, this formal definition is that you have a prices, and at these prices, every agent is going to demand a bundle that minimizes their disutility subject to their earning constraint. P dot Y is how much they earn, right? Pj is the price per unit. Yj is the amount they get. So Pj times Yj is the price they have to pay for that, they earn for that amount, and you sum it up. So this vector product is the earning, and that should be at least 1. Subject to that, they minimize their disutility. This is the optimal bundle. Okay. And once everybody gets their optimal bundles, demand should be equal supply. That means for every item j, the sum of the xij is the amount of item j agent I gets, right? So this sum over all agents I should be exactly 1. This was the supply. So mathematical definition of equilibrium is clear. Optimal bundle, minimize the disutility subject to earning constraint. And then once everybody do that, you aggregate the demand for every item. It should be exactly equals the supply, which is 1. Okay. Okay. So now on, whenever we say X is feasible, we mean this constraint mathematically. Okay, we're going to focus on feasible X always. Okay. So this is what I mean by feasible X. For every item, you have demand equals supply, and it's of course an allocation, so it cannot be negative. Okay. So these guys said that let's minimize the product of disutilities, Nash welfare. But does Nash welfare really make sense when you are trying to minimize stuff? What's the optimum? 0. Because you can choose one of the agents, your favorite one, give them nothing. Their disutility will be 0. Now you give anything to anybody, the product is going to be 0. Doesn't make sense. Okay? This is the catch. You have to minimize the product subject to open constraint that everybody should get a non-zero disutility. No, there'll be the dual variables. Dual variables to this. The prices will be the correct. Yeah. And this is, and so product is very difficult to work with. So let's apply log. Log is an increasing function. If you are minimizing something log, you're still minimizing log of that. That's equivalent. So when you apply log to the product, it's the sum of the logs. And this is exactly, really resembles the Eisenberg-Gill convex program for the goods case, right? Exactly, just opposite, maximizing the sum of the log of the values subject to the feasibility constraint. It's an open set. That's the catch. Big catch, right? So, okay, now to answer your questions. So this hopefully already answers somewhat your questions. What they prove is that if you look at the Pareto optimal frontier, so this is a downward frontier, right? The minimizing frontier. The point on the Pareto optimal frontier where the product is maximized is an equilibrium. Feasibility constraint. Always be in a feasible space. Yeah, so Pareto optimal frontier subject to the feasibility constraint. You look at that. On that Pareto optimal frontier, you maximize the product of the disutility. So basically, you are trying to equalize the product of equalize the disutilities as much as possible while remaining on the Pareto optimal frontier. Right? When you try to maximize product of some values, you're basically trying to equalize those values intuitively as much as possible. Okay, that particular point is an equilibrium. There might be many others, but this is one of the solutions. Make sense? Okay. Does that answer the question, Rohit? Umang? Yeah. Something happened. I'm fine. Okay. So the convex program for Eisenberg is a nice, happy because convex program, you have a global optimum, look and find it. Yeah, nice, everything nice. But when you are minimizing a concave function, that's a non-convex program, right? And you are on top of that, you have open constraints. Am I doing something with the microphone? Okay. So this is non-convex program, and on top of that, we have open constraint. But the catch is that we only want a local optima. Okay, we are not after a global optima. Global optima might be hard actually, NP hard. Okay, we are only after a local optima of this program. Okay, and that's why we may have multiple solutions. The local optima thing gives us multiple solutions. Okay, so basically if you have really worked out details of how Eisenberg-Gale convex program gives you CEI, you will see that you only need KKT conditions to get the CEI conditions. Okay, and KKT conditions are essentially just local optima. Okay, so that's why you only need local optima of this program to find a solution. Okay, now let me give you a geometric view because this will be very useful for our algorithm. What do we mean by local optima geometrically? So you have, now I'm going to switch to feasible disutility space. So given any allocation, you will get a feasible allocation, you will get a disutility point. So you are projecting to the disutility space now. Okay, so now just focus on the disutility space. It will be nice convex space. And you are trying to minimize this sum log. Okay, what is a local optima? You look at the gradient of your objective. Okay, and this point is the local optima. If you look at the supporting hyperplane's normal, that should be proportional or equal to the gradient. That's the KKT condition. Right? That's the local optima condition, because if you have that, now at this point, locally, you cannot decrease the objective. Because if you try to move in any positive direction with the negative of the gradient, because that is where you will move to minimize, right? Then you will be always, so any positive, any direction that makes a positive angle with this negative of the gradient, you will definitely go out of the feasible region. Does that make sense? Yeah. And that's why this is the local optima condition. Okay. Look at the supporting hyperplane at that point. Look at the normal. The normal should be equal to the gradient at that point. Okay. It is a characterization. It is their BMSY characterization. The entire thing is this, yeah. This is the BMSY characterization. Okay, so
Right, in the sense that like optimum without this, without this constraint on dx is just clearly LC to G.
correct.
But somehow you're saying that if you just have this open set, the optimum shifts all the way to some, non-limiting point.
Correct. I mean, yeah, it's very natural to think that why don't we put a constraint like every dixi is at least some epsilon, where epsilon is 1/2 to the n or something, right? The point is that you will get a doer variable for this constraint, and that will break the commutative equilibrium condition. So you really need this KKT point, right? You don't want any extra constraint because the dual variable of that constraint is going to mess up the the KKT conditions and CEI, like you'll not get CEI.
What's happening is that your feasible set, you know the objective, but the gradients at the axis, but D is positive means you're just looking at the
Positive ortho.
Positive ortho.
Yeah.
And disallowing the
axis.
At the standard axes, you do have orthogonality with respect to
The axis aligned hyperplanes.
gradient.
Yeah.
But very close to it,
It's not, yeah.
It's kind of like the Lipschitz condition for log. But close to zero, it's very bad.
Yeah.
It starts behaving very well and goes very far.
Yeah, it's very weird actually, but pain.
Yeah.
They are pain.
So,
Yeah, they are chores. We got into a chore improving for chores. I mean, yeah, this problem has haunted me for the longest time. I took like 2 years to really. So I wanted to give you this proof. It's a very cute proof. It's not very difficult. Why this characterization gives you a CEI, but I have like, yeah, less than 10 minutes. So I'm going to skip, sorry. But the point is that we can prove that if suppose your normal is not exactly the gradient, but approximately the gradient, then you still get an approximate CEI. Okay, and that's what we'll be after now. So now let me quickly show you the algorithm. Okay, so first thought is to apply gradient descent. Local optima of a non-convex program, what do? Apply gradient descent, of course, right? Yeah, that would not work. The problem is this open constraint, right? So look at this objective. You're trying to minimize some of the logs. When you're minimizing this, your gradient is 1 over di because of minimization, you'll try to move in the direction of 1 over minus 1 over di. So what will happen? The smallest di will have largest value for 1 over di, and that's why that will decrease the fastest, right? Any variant of gradient descent you try to do, you will be going into this kind of situation. Okay, smallest di or smaller di's will be decreasing fastest. Okay, and you apply log barrier functions to avoid boundaries no matter what you do. This is what happens. We tried experiments, we tried many different things. Always go to that open boundary, like where you're trying to avoid. Okay? And it's natural because, I mean, global optima lies there if you forget about the open constraint, right? So it's natural for gradient descent to go there, right? Okay, we were like, okay, I give up kind of, right? Then it struck to us that how about doing something from the exterior of the region? Okay. Non-convex, the problem, but let's see, at least there's something that could be nice is that if you look at the lower exterior region, so first of all, this is a full dimensional, in the disutility space, there's a full dimensional polytope. Okay, feasible disutility is a full dimensional polytope. And you can talk about something called lower hull of this polytope. This is the lower frontier, petro-optimal frontier, right? And you can talk about the area in the positive orthont below that. And in that area, forget about non-convexity, but in that area, if you try to maximize the objective, then local max in the exterior is same as local min from the interior. It's the same KKT condition. Normal to the supporting hyperplane should be proportional to the gradient, the same condition, whether you look it from the exterior or you look it from the interior. Okay. Okay. Yes. So then you can really move in 1 over di direction because now you're maximizing from the exterior. So you'll be moving in the 1 over di, the gradient direction, not the negative gradient direction. That will increase the smallest di fastest. This is what you want, to go away from the boundary, right? Okay, fine. This thing is well defined only in the disutility space. So you have to keep going back and forth between allocation and disutility. Non-convex, of course, right? What should be potential function? How do we show fast convergence? We have to answer all of these questions. So first of all, let me convince you that we really, so I'll give you a method through which we can really decrease this objective function. So this is the potential function of our method. Okay, let's start with some exterior point. And let's say I project to the nearest boundary point of the polytope. Okay. First thing I can prove is that if D is the nearest boundary point, that it is pointwise superior than E. Okay, it coordinate-wise increases or remains the same. That means I'm going to either keep this objective as is or increase it when I go from E to D, right? The next thing we do is that we look at the supporting hyperplane, okay? Either you already are at an approximate KKT point, then you're happy, you stop. If you are not, then look at the supporting hyperplane and try to maximize this objective only on the hyperplane itself. Where would you end up? If I maximize some of the logs of DI, subject to only being on this hyperplane, forget about all other constraints. All feasibility constraint, blah, blah, blah. Forget everything, non-negativity constraint, everything. You are allowed to go anywhere on this hyperplane, even in the negative orthorhons. So, but you have to maximize the sum of the logs of DI. Where would you have? It will, so first of all, you are in the supporting hyperplane, so you can't go on the interior. Exactly. So you have to remain in this exterior region. You will never make any coordinate negative because you are maximizing a log. You will not even make it 0, right? You will not even make log of 0 is minus infinity, so you will not even go there, right? So you will always remain in the positive front and you will remain in the below because you are on the supporting hyperplane. So again, you will end up at another exterior point, right, E prime. And by definition, because we maximize this, either the maximum was already here or you move to a better point, right? So you must have increased. If you really moved, you must have increased this objective. If you didn't move, you can prove that it must have been your solution. Okay, that's it. Just two-step algorithm. Keep repeating it until you reach a solution.
You start off with this region, but with a non-convex objective, which is minimizing log. You swap that for a convex objective, which is maximizing log, but it's a non-convex. But the interesting point is that this switch does give you a lot of algorithm.
Correct. Exactly. Just change in perspective. Yes. Yeah. So this is the algorithm. You start with an arbitrary exterior point. You project to the polytope, the disutility polytope. Either you are at a solution. If you are not, then look at the supporting hyperplane, maximize, and you can actually prove that the grade normal to the supporting hyperplane is going to be exactly this direction because it's the nearest point. That's why. Okay, ET minus DT direction. And if not, then you maximize the sum log objective on the supporting hyperplane. You get the next exterior point, and then you repeat. Okay, I'm done with my time. Okay. Do you think this has to converge? What if every time your improvements are very, very, very tiny? Right? You can have an improvement of 1/2, 1/4, you can have a converging sequence, but you will really never make it to the solution, right? Yeah, you have to prove all of these things. So if you converge, you're sure that you are at a solution because you will stop only if your normal is proportional to the gradient. But we do have to prove that you will converge in polynomial time. You will actually, yeah, in finite time and then eventually in polynomial time. And for that, we prove that you, in the second step, where you maximize the sum log objective on the hyperplane, if you are not an approximate equilibrium, then you make at least so much progress in your objective. Okay, and then the objective is upper bounded, so that's why you get a finite convergence. The intuition behind this main lemma is that if you are not at an approximate solution, then your gradient is quite off compared to approximate, your normal is off than approximate gradient. What in the market term it means is that every agent is really buying their optimal bundle, but their budgets that they are earning is off by more than 1 plus epsilon. So budgets are imbalanced. When you maximize the sum log objective on the hyperplane, you balance out the budgets. Okay, but now you are not keeping track of the supply demand constraints. You are outside the feasible space. Okay, so some chores might be over allocated, some chores might be under allocated, and so on. But when you balance out the budget, you balance out the disutility that increases the product of the disutilities. Okay, and that's basically the intuitive argument. Okay, we have the extensions to one homogeneous, but let me just skip through this. I think I really don't want to eat up on the next slot. So this was another beast, actually. We got this algorithm for additive, but for arbitrary one homogeneous, because the function is not explicitly given, it's a black box oracle, right? You give the bundle, it tells you the value. So you have to do approximation at many, many fronts. And finally, we have to show that these errors don't accumulate. Sorry? Yeah, good. So we have to keep track of this, whether you are at a feasible disutility or not. For that, you have to go to the allocation space and check whether this utility can be achieved at some feasible allocation or not, right? So, no, it's the same thing for the non-additive as well, because DI is not DIJ, it's a DI. Yeah, so all of those things remain. I think this just going between actually solving nearest point is a convex program, right? You are at exterior point, you find the nearest feasible point, that's a convex program. But that you can solve exactly if the constraints are linear, right? So, and so supporting hyperplane, all of these, like you can't have an exact supporting hyperplane, your supporting hyperplane will be approximate. So when you are in a black box model for the valuation functions, is much more complex. But you can do it. And yeah, let me take the mixed case offline and let me stop here. Thank you. Questions? Okay, I think we have had quite a few questions during the talk, so maybe we can take the rest. Do you need this, Nisha? This is mine, but I'm not sure if you want. Yeah.
We have that.
Okay.
It
Okay.
was working, so that's okay.
No.
Is it working?
Yeah, it works.
It's easier to plug it here, something more responsive.
Yeah, this side, I think.
Okay, so the next speaker is Manisha, and she'll be talking about crowdfunding.
Is this good? Yeah. Are you able to hear me? Thank you, Sudarshan. And I must thank the organizers for having me here and organizing such a wonderful workshop. Thank you. Thank you so much. So today I'll be talking about provisioning public projects. I think we have already seen this quite a bit yesterday in the context of participatory budgeting. So today I'll be talking about that in a slightly different setting. And in the context of welfare maximization. So we'll see that with even a very minimalistic fairness requirement that all of the agents should have at least non-negative utility, this turns out to be quite a tough thing to deal with. So that's what we'll be sticking to today, welfare maximization with a very minimalistic requirement of non-negative utility to each of these agents. So I'll be motivating civic crowdfunding, and then I'll describe the problem setting. And I'll be talking about two different settings. One is the centralized setting, which is the more familiar topic of participatory budgeting, where there is a central budget and a central planner trying to allocate these budget to different projects. And the other setting is decentralized, which is more common in the civic crowdfunding literature, wherein agents come and they voluntarily contribute to the different projects available. So that's how that's the broad sort of division of crowdfunding that I could think of. And finally, summarizing the whole and some future work. So civic crowdfunding. So civic crowdfunding has two key aspects to it. The first thing is civic, that means pertaining to the public or some local community, wherein the projects that we talk about could range from any public project like parks or libraries or roadways or canals to some welfare-oriented projects, like you want some health benefits for the local community, or some other social well-being projects, etc. So we are talking about funding for these projects. Typically, the government is the one which takes, the local, central, or federal government, which takes initiatives for funding these projects, but oftentimes governments lack the funding or the resources to make these things possible. So that's where the next word comes, the crowdfunding. So we want the crowd to come together and fund for these projects. So the main idea is to get the people together to come to a consensus to fund a particular project that apparently the society or that particular community needs. So that's the idea of civic crowdfunding. And these are two very well-known examples. So the wooden pedestrian bridge in Rotterdam. This is in Netherlands, where the local community, the local people were very unhappy about so it took them a lot of time to reach to the city center because of the busy roadways and the railways. And the government was not really doing much about it. It's similar to the Bangalore and Hyderabad problems, I say. So they took it upon themselves to construct this wooden pedestrian bridge. They funded it, that particular city, the people came together to fund it and made it possible. The other famous example is of this One Belt, One Road initiative by the Chinese government, wherein they want to build this one big, large corridor that connects west of Europe, east of Asia, and some parts of Africa to enable trade and things like that. The problem is this project sort of is across multiple continents and different countries. So it is no way one country can handle all of this project of this scale. So all of the other countries must pitch in terms of workforce or resources, etc., to be able to make this possible. So that's the setting that we are dealing with. So in crowdfunding, people are interested in multiple projects. There are some requirements that people have, but the goal is which of these, and of course there is not enough money to fund it all and make everybody happy, but what we want to know is which of these can we fund. Now this sounds similar to the setting of resource allocation, wherein we have different items and people are interested in these items, and we want to allocate these items among the people, but there is fundamentally a difference in this particular setting, in the sense that the project that we are interested in is non-rivalrous. That means once the project is funded, everybody gets to derive utility out of these projects. There is no notion of membership or ownership to these projects. Everybody gets to use these projects. And in fact, they are non-excludable. That is, you cannot stop people from using it. Let's say there's a public park that we have funded, or the wooden bridge. You cannot ask people, oh, look, you have not funded while we were conducting this crowdfunding, so you're not allowed to use it. That's something we cannot do with these projects. So that's what sort of sets it apart from the regular setting. Yes. Not necessarily. It's not necessarily, not in all. There is a slight difference in the participatory budgeting setting, which I'll be talking about. So in the participatory budgeting setting that we are more familiar with, what we assume is that people have already contributed at some point in the past. We don't know who has contributed how much, but we assume somebody has, and now we have a central funding, maybe all the tax accumulated together. Now, the goal of the central planner is to just come and decide how to use these funding, how to use the available funding for each of these projects. So here we assume that all of them have contributed to some extent, but we don't know who has done how much. Now, the goal of the central planner here is, first the people will come and vote for their preferred projects. And the central planner's task is to aggregate their votes and to fund a desirable subset of projects. Desirable, we don't know what that is, but yeah, desirable subset of projects. That's the goal of participatory budgeting. And all of the existing work in this centralized framework, they do not really model agent contributions. The agents don't care about how much I have contributed more, so more of what I wish I should have a more say in what happens. That's not how existing work looks at it, as of like majority of the existing work, I would say. So we would like in our work, what we would like to do is to look at a generalized version of this, wherein wherein again the people come and vote or give their preferences. The goal is to aggregate the vote. And also the central planner has one additional task. The additional task is to specify each agent's contribution. So how much should each agent contribute? Now, all of these agents come with a budget constraints. They cannot contribute more than a certain budget. If you add up all these budgets together, that should be equal to the central budget that is there at the expense of the central planner. So that's how we sort of relate it. So each agent has a budget constraint. The sum of the budget is actually equal to the central funding that is available. And the central planner is now also going to take into consideration how much each agent can contribute, and with that is going to propose which set of the project should be funded and how much should each of the agent contributes under the budget constraints. We are introducing. Sorry. Exactly. The entire money pool here comes from the agents. So sorry. Okay. So agents care about where their money is used. And there are a couple of works which in the participatory budgeting context look at this particular aspect and model contributions. But they typically look at the continuous project case wherein so here we are interested in indivisible projects wherein once the target cost is met, only then the project is funded. But you could think of some other projects like maintenance or maintenance of an existing resource that is already constructed. So you can contribute any amount of money to it and you will get a linear some function of utility out of every unit contribution that you make. So yeah, that's what the existing work look at. So our goal here is for this generalized PB setting, we want to fund a desirable set of projects in the new model. Yes. Infinite budget case, like if each of the agents have sort of infinite amount of budget, then it will sort of capture the existing. So yeah, so this is the setting. This is one of the aspect of civic crowdfunding, but the other aspect that we also do look at is this decentralized civic crowdfunding, which is sort of more common. That is something that we all are familiar with in these platforms like Kickstarter or things like that, where agents arrive at the platform. There are multiple projects that are being crowdfunded, and we all know how much of contribution has happened to each of these projects. Based on that, we realize certain valuations for each of these projects, and then we voluntarily try to contribute to these projects. So this is what, so there is no central planner trying to specify how much to contribute. We just come and contribute based on our wish and our budget to each of these projects. Of course, the catch is that the public project setting, the projects are non-excludable. Once the project is funded, even if you have not contributed for it, you get to use it. So in this particular setting, it can happen that agents really don't have any incentive to contribute. They would want to free ride, because once the project gets funded, you're anyway going to you get to use it. And there are enough people, you feel that there are enough people to contribute to it. So then you would not want to, you're not incentivized to contribute. So here, what we try to look at is we want to raise enough funds for funding the desirable set of projects through incentivizing agents to contribute to it. So there are two parts of it. In the centralized setting, we assume that agents are truthful. They come and vote for the projects. They report it truthfully what their preferences are. And our goal is just to sort of aggregate these preferences. In the other setting of decentralized crowdfunding, agents may not be incentivized to, be truthful. So we have to introduce incentives in a way that we are able to fund the projects that people want or all of us want, something like that. Yes, it's welfare. Yeah, it's just, yeah, I will. Yes. So so for example, here we are looking at a notion called weak participation. That is just, it should happen that at the end we should fund a subset of projects such that none of the agents should incur negative utility. Like they should at least get a value more than what they have paid for. That's the weakest possible notion that you could think of. Yeah, quasi-linear utilities. Yes, we are in the quasi-linear domain, and yeah. Just that's it. So which is more commonly referred to as individual rationality, but in the participatory budgeting literature, individual rationality is something more strictly stronger in the most of the work that I could see. It's like if an agent takes its own budget and funds a different set of projects with his own or her own budget, and the project that particular agent could fund gives that agent more utility than the selected subset, then that is referred to as individual rationality, which is why we are calling this particular notion of, which is the notion of non-negativity, is even simpler, right? So we just refer to that as weak participation. And in the decentralized setting, that's anyway that is something we get for free, because agents won't contribute more than what their potential value could be. That is something, they are strategic, so they can do that. So we are just worried about welfare maximization, social welfare, utilitarian maximization. Yeah, that's it. Yes, exactly. Taking it, while ensuring these two properties. Yeah, that's it. I hope the setting is clear. So this is the broad flowchart. We have crowdfunding, the centralized crowdfunding, which is more commonly known as participatory budgeting. There is a pool of budget, and the central planner aggregates the votes and also specifies the contributions. And we consider discrete multiple projects. By discrete, I mean there is a fixed target cost to each of these projects. If the total contribution to this particular project exceeds the target, the project gets funded, otherwise it doesn't get funded. And that's the setting that we consider. The agent's role is in centralized setting is just to vote for the project and be honest about it. That's it. That's what we want. And what we desire is that we want the welfare optimal, the social sum of the subset that gets funded should maximize the sum of utilities of all the agents. And the weak participation notion, which I'll be defining soon, that is every agent should at least get a non-negative utility out of participating. In the decentralized setting, we must have refunds, otherwise we cannot really, there is no way the central planner can communicate with the agents here. So the central planner introduces refunds, assuming that he has some additional amount of budget or bonus to work with. Some very small amount of bonus to work with, but not enough to fund the projects, for example. So that's why I'm talking about no budget pool. And also the central planner doesn't get to specify the contributions. Here again, the same setting of discrete multiple projects, and agents come and they are strategic. They can, based on the kind of incentives that they are getting and the kind of projects, kind of interest that they have in different sets of projects, they can contribute accordingly. And here also we are looking at welfare maximization. And so at equilibrium, if agents do what they want by being strategic, are we able to ensure that we can get the welfare optimal set funded at equilibrium, under equilibrium contributions? That's the kind of thing that we are looking at. Of course, it definitely ensures weak participations, because agents get to contribute. Yes. No, we do not assume. So so here typically crowdfunding is not a simultaneous game. It's like agents come sequentially and contribute, but here in this work that I'll be talking about, we are treating it as a simultaneous game. All of them have to contribute at the same time. So they do not really get the time to strategize that way. Oh yeah, so the equilibrium contributions sort of have an upper bound, like you can contribute that equilibrium contribution or whatever money that is left to get the project get funded. If if the value comes to be more than that, you don't have to fund it, like contribute the entire money. Just contribute less than that. So yeah, here we are considering a simultaneous game. So I do not really know what the other agents' contributions are in this setting. So it will be a more advanced set. So there are advanced follow-up works where they look at it as a sequential game, and what you say makes more sense there. So these are the two works that I'll be talking about. They are like sort of independent. Agents report their valuation truthfully, and then it's a matter of preference aggregation. And in part 2, agents is the decentralized version where agents might misreport their valuations, and we have to study what the incentive schemes can really offer us in terms of welfare maximization. Yes. Any questions or doubts in the model? Okay, so let's move on. So agents report their values truthfully. This is an instance of participatory budgeting itself, where there are n agents and each of these agents have a budget P. The central budget is the sum of all the individual budgets. We have an M set of projects, and each of these projects has an associated cost. And we consider additive valuations, not just binary, it could be any real number. So Vij is the value that agent I has for the project J. And we are interested in determining these contributions. How much should each agent contribute? For Xi is a vector where the contribution Xi represents all the contributions for each of the M projects. And the contributions will help us then determine the set of projects that get funded. For all of those projects where the contributions exceed the target cost, it is deemed to be funded. So that's the W set. And we consider a quasi-linear utility model wherein the utility of the W set getting funded is equal to the valuation minus the contribution that the agent has made. So this sort of allows us to, including this in the utility sort of allows us to ensure that agents do care about the contributions to contribute in the project that they really care about. So this is slightly not common in the existing literature of PB.
It's like per project, not like give one, like Xij is not just a single number.
Yes, it's not it's for each of the projects, each of the J in W.
It might actually have negative for others.
That is fine. That is, but overall it should not be negative. Yeah, that's what we. So preference aggregation for this particular generalized model. So we are given an instance and we are looking at UWO by utilitarian welfare optimal solution. That is, it maximizes the sum of utilities under the budget constraints. And I think it's fairly easy to see that UWO is NP hard even for single agent case because it can be reduced from the standard knapsack wherein there is a budget constraint for that single agent and has different valuations for all of these different projects. And it's just about solving the knapsack for that. So we do have an FP task for this, but with the additional constraint of weak participation, that is non-negative utility to each agent, what are the guarantees that we have? That's what we study in this particular work. So yeah, more formally, we are trying to maximize the sum of the utilities such that the budget constraint is satisfied and each of the agent gets non-negative utility. The utilities are quasi-linear. Yes. So the results, yes. Yes, it is. I mean.
So you just want that finally the sum of the.
Exactly. Exactly. Total contributions. Yes. Yes, yes. Yes, that is also true. For each agent, they should not. that each agent should not contribute more than their budget. Xij is less than, do I want that? Yes, so I have this constraint that the total, yeah, that is true. That has to be here. That has to be included. Each agent cannot over contribute, like contribute more than their budget for sure. Cost of the W should be less than, so this is what I want. I don't want the total cost to be more than the total budget that I have, which they, no, it's just the budgets, some of their Bs. Yes, BIs are given to me as the part of the. Yes. Okay. So the results are that there is no polynomial time approximation for this particular problem, UW or WP. And there is, in fact, no polynomial time approximation even for the identical cost setting. That is, if all the projects had the same cost, even then it is tough to have a polynomial. It's not possible to have a polynomial time approximation. But it does admit an FP when agents are laminar single-minded. Now, what is laminar single-minded is something that we are familiar with, wherein each agent has a utility, has a positive utility for a bundle or any superset of that bundle, but and zero utility for every other possible subset. That is single-minded. Laminar single-minded is slightly stronger than this particular entity. If there are, so we are able to only show FPTAs for strictly very restrictive setting. If two agents like a particular bundle, that bundle has to be completely same or has to be completely disjoint. So they cannot like subsets of each other's bundles. They have to either like entirely the same bundle or entirely the different entirely different bundles. So that is laminar single-minded, and for that it does admit an FPTAs. So I'll slightly give an example to see how we come up with the polynomial time that it is in that does not exist a polynomial time approximation. So for that, I would like you to look at this example. This is an instance with 2 agents and 4 projects. There is a sort of an agent who is coming with no budget, but a very high value for one particular project. So, to have a utilitarian welfare solution, this project must be part of that solution because it has a very high H is a very large number here. So if the W or the set that we fund is only the first project, that is project 1, then what we can see is that we do get a very high value welfare of H, but agent 1 is the agent with a budget of 2 and must contribute at least 1 for this particular project to be funded, and thereby agent 1 will get a negative utility out of this because agent 1 does not really value project 1. If project 2 is funded, both of the agents get positive utility. Agent 1 can fund the project because the budget is enough for that, and the value that the agent 1 gets is 20 minus 2, which is 18 and not so high. You could do better. So if we fund project, so now we could try funding each of these projects 3 and 4 as well, and we'll not end up getting a very high value. But there is one interesting thing about these 2 projects individually. If I try to fund project 4, then so agent 1 can definitely fund it and have a utility of 2 by funding it. And so 2 minus 1 has an additional utility of 1 still remaining, and that utility could be used to fund project 1 and grab this very high valued project. But instead of funding project 4, if we chose to fund project 3 first, at this step we could have had a lot more utility because of this 20 sitting here. But agent 1 would lack the budget, enough value to, so because this particular project just agent 1 values it at 2 minus epsilon, after spending $1, there is only 1 minus epsilon value left. So if we fund project 1, agent 1 would be at negative utility. So after funding, greedy approach will definitely not work. Like if we fund project 4, which is less valuable than project 3, we are in a better position to fund project 1 than when we fund project 3. So the goal is to try to find a subset of projects that ensure us to extract this maximum value left, so that if there is a very high valued project which is not affordable by the agents who value it, we are able to fund that, so that we can then use that to increase our total utility, the social welfare. So that's sort of the idea. So what we define, this new problem, we define it as maximum excess payment extraction, wherein we would like to fund a subset which extracts the maximum amount of value left. So it could be if I have enough, but if I do not have enough budget, then that budget is what is sort of limiting me from extracting the value. If I have enough budget, but I do not have enough value, then that value is sort of restricting me. So taking into that, considering that, we would like to fund a set of projects that sort of extracts the maximum value out of the funded subset. What we show is that we can use any polynomial time approximation to the problem, our desirable problem of UWOWP, and use that to decide whether we can extract at least T unit of value from this setting. So, so essentially, we are trying to reduce max PE to a polynomial time, to any polynomial time approximation of UWOWP. And then we show that it is NP hard to compute max PE even for single agent by reducing it from the partition problem, thereby making it, we do not really have any polynomial time approximation for this particular solution. So this particular statement is sort of, so how do we show the equivalence, like we show the reduction from max PE to UWOWP? We consider an instance of participatory, like the NMVBC, the standard instance, and we design a new instance IT, wherein we add a dummy agent 0 and a dummy project 0. The value that the agent has for this dummy project is very, very high. It's more than the total valuation that of the old instance, the total, so the valuation that each agent I has for this grand bundle, sum it across all the agents. This is the total valuation that one can have in that old instance. And we multiply that with this polynomial factor. And this dummy agent practically has no value, has 0 value for all the other projects that are there. And all the other agents have 0 value for this particular project. And this particular project costs at least T. We need to fund this project, we need to extract T unit from the old instance. That's when we can fund this particular project. So what we show is that for this instance, if we have a polynomial time approximate algorithm, ALG, what we show that if that algorithm yields a utility of at least twice the total value that one can have, we can ensure that max PE, we have for sure that max PE for the old instance is at least T. Sort of easy to see. It's the other way around is also, if we can extract T amount of T unit of money from the old instance, we can ensure a welfare of at least twice the project. So this is how the equivalence is shown by constructing this example. And thereby, we prove that there is no polynomial time approximation even for the, so for this particular problem of UWOWP. Yes. Any polynomial function. Any other questions? So for the special settings, in the case of laminar single-minded setting, what we see is that it admits an FPTAS. Actually, the max PE becomes is a hard problem in the previous setting as we reduced it from the partition. But for single-minded agents, it actually becomes polynomial time solvable. But we are only able to show FPTAS for the laminar single-minded setting by reducing it from knapsack on conflict graphs. But it's still open. The single-minded setting, getting any bounded approximation algorithm for single-minded agent is still sort of open. So yeah, these are the results from the centralized participatory budgeting setting. So if there are any questions, I'll be moving on to the next setting of decentralized and strategic agents. If there are any questions from here, I can. Yes. Yes, not really. It's still, yeah. We looked at identical costs, and that also turned out to be sort of inapproximable. Yeah, and then we have to still look at other valuation functions. They're probably doable. And of course, other utility notions as well. So yeah, now we consider the decentralized setting. We'll change gears a little bit. It's a very different modeling, which is more common in the civic crowdfunding domain. So here we have the same model. We have N agents, B budgets. Each of them has a budget B, M projects. Each of the project has an associated cost, valuations. But on top of all of this, we have an additional in quantity called the bonus. The bonus allows us to allows the central planner to intervene into this particular game of contributing to the favorite project, and the bonus is what the central planner spends to offer incentives to people to contribute. So now in the outcome, what we have is we definitely want what is the set of projects that is funded, but we also would want to define a particular refund scheme which is based on this bonus, such that looking at the refund scheme, I know I being an agent, I'll see, oh, this is the amount of refund I'm going to get upon contributing to so and so projects. So how much should I contribute so that I maximize my welfare? My welfare being either the refund or the value that I'm deriving from the project that is getting funded. So sitting here, I'm trying to contribute this optimal X star that maximizes my utility for me. Now, our goal is that while agents do that, strategize that, we want to ensure that when they do that, the project gets funded. That's how we want the refunds to be constructed, that when agents strategize and contribute their equilibrium, our desirable set of projects should get funded. That's how ideally should be designed. So in the single project case, it has been studied by Zubrikas in 2014. Zubrikas presents this refund scheme called PPR, which is Provision Point Refund Scheme. And they basically introduced this entire concept of refund scheme, and they in fact also try it out in various ongoing real world public projects, and see that after offering incentives, they are actually able to ensure the funding of many more projects than it could have been possible without offering these refunds.
Give them back to the agents, or you subsidize certain projects?
No, give them back to the agents. In effect, subsidizing, yeah. The bonus is not enough to fund any project. So yeah, that's something. It'll be clear. So when the project is funded, the value that an agent derives is VI minus XI. Single project case, there's only one project. The value that agent has for the project and the contribution it's made. If the project is not funded, this is where the bonus, I'm sorry for the type, this is not budget, this is the Math Cal B, the bonus. So this is what the agent is going to get as an incentive. It is proportional to the agent's contribution, and so it's going to get a fraction of so with capital T is the total contribution made to the project. So this much fraction of the bonus is what the agent is going to get as an incentive when the project is not funded. So this is the utility structure, more the contributions. So, okay. So by non-quasi-linear, you mean? F of xi. So this definitely makes it easier to analyze the effect of refunds. But yeah, probably that could also be a more general way of representing it. Some sense. So this is. So this is the overall utility. When the project is funded, when the total contributions is more than the target cost of the single project that is there, this is the utility and the total utility that the agent gets. If it is not enough, then this is the unfunded utility that the agent gets. So yes, this is for a single project. Oh, that is returned. Oh yeah. If the project is not funded, whatever contributions you have made is returned. On top of that, you're getting this as the additional value, like additional incentive in some sense. Yeah, sorry. Yes, yes, exactly. You positive. Yeah, assuming there is some bonus aside. Yes. You get the total value V.
Pay people to participate because their opinion matters, but they are poverty stricken.
Pay people to participate. So
Don't have the money, but their PIs are negative.
then I mean in this model, so if let's say the project doesn't get funded and they don't have any money, they don't contribute, so they don't get any refunds. So this definitely doesn't cater to such kind of people. If you don't have money, you're not welcome in some sense. No grad students. So the idea is if there is enough value for the project, then it does get funded at equilibrium. That's the thing about PPR for the single project case. And the equilibrium contributions can be derived in this way. Xi bars is what I denote the equilibrium contributions to be. And each agent, so this if you remember, I said is a simultaneous game. All of them are contributing at once. We don't really know how good so if had we contributed it sequentially, we know, oh, there is enough interest for so and so project, so maybe I could contribute more in that or less in that. Such kind of analysis we cannot do here. We assume there is a 50% chance of any project getting funded and 50% chance of it not getting funded. Oh, am I out of time? 5. Oh, okay. So the deriving equilibrium contributions is by ensuring that by making the funded utility equal to the unfunded utility. So if there is enough valuation that the total value is at least the total cost, then the total contributions will become at least the total cost after solving this particular equation. If you exceed it, then you don't really have to contribute Xi bar. You can contribute less and get the project funded. What we show is what in the subsequent paper, Damle et al., they show that any refund scheme that satisfies contribution monotonicity, that means as long as your refunds increase with respect to your contribution, the project will get funded at equilibrium. But the main catch is agents may not have budget to give the equilibrium contributions. That's the idea. That's what we look at. We look at the more sort of strictly more general case wherein there are multiple projects, each of these agents have budget restrictions, they cannot happily come and contribute the equilibrium contributions. So now are we able to fund the welfare maximizing subset, which we call, are we able to ensure a SEE, socially efficient equilibrium, is what we are trying to study. So what we, so can we have an any incentive scheme that satisfies contribution monotonicity, guarantee SEE? That means if you contribute more, you get more refunds. Such a refund scheme, can it guarantee SEE? So what we study is these two different settings. When there is enough budget in the system to fund the welfare optimal subset, can we ensure SEE when there is so when there is enough budget to contribute all the projects. Let's say there is enough budget to actually fund all the projects. A central mechanism would do a better job in funding all those projects here. But when the agents are strategic, what we show is that without this without this additional constraint of subset feasibility, we cannot guarantee SEE, even though there is enough budget in the system. If without the with the condition of subset, only with the condition with the guarantee of subset feasibility on top of budget surplus, we are able to guarantee SEE. And without, of course, when there is deficit of budget that we cannot fund all the projects, we can only fund a subset of it. Can we then guarantee SEE? What we show is that it's not possible. SEE is not guaranteed with any refund scheme that satisfies CM, which is a very basic requirement. So this is the sort of the summary of the results that we have. And I think I should. So when there is budget, so what is subset feasibility? So this is a very easy notion to sort of understand. So we had derived those equilibrium contributions, right, xi bar, by equalizing the funded utility to the unfunded utility. So if each agent has at least enough budget to contribute that particular equilibrium contributions to each of these projects, then subset feasibility is sort of ensured. So it is essentially like running multiple single projects project civic crowdfunding instead of clubbing them all together. And we ensure we are guaranteed that by running, since agents have enough budget to contribute equilibrium contributions to each of these projects individually, you ensure that all of them get funded at equilibrium. That's this very simple case of budget surplus and subset feasibility. But if there is no subset feasibility, equilibrium contributions actually may not exist. Because let's say agent one, because okay, should I? So the idea is that the equilibrium contribution may not exist because agents do not want the project to be funded, because the utility from not getting the project funded is strictly more than the utility when the project is funded, if you contribute more than your equilibrium contributions. So which is why agents are incentivized to ensure that the project does not get funded, which is why they keep contributing epsilon more to grab more refunds, but not enough such that the target cost is met, which is why it's not possible to define equilibrium contribution in this particular setting. And this sort of carries forward in the case of budget deficit as well. And we show that so this sort of also contributes to the fact that guaranteeing a socially efficient equilibrium is not possible in the case where budget is deficit. But all of this is assuming that the agents are strategic and smart and are able to do optimal deviations. But what we show is that deviating optimally for an agent is also very tough in these settings, because there is incentives and all of that. So trying to determine what is an optimal deviation for an agent is also NP hard, and we reduce it from standard knapsack actually for some instances at least. So yeah, this is summarizing the results. When agents are truthful, it is inapproximable to, preference aggregation itself becomes inapproximable. And only for the setting of laminar single-minded agents, we have an FPTAS. When agents are strategic, we cannot guarantee SEE, that is UWO, to be funded at equilibrium unless for a very specific case of budget feasibility and budget surplus. So yeah, this is it. And so there are like plenty of open. So this is just a beginning of the work. There are so many fairness measures and welfare measures yet to be explored. So bounded approximation for the single-minded setting is still an open problem. And like Sir said, like there are other restrictions that could probably bypass the inapproximability that we had there. We could also look at approximations to the socially efficient equilibrium that might exist, and other welfare. Can we design refund schemes to guarantee fairness, or other welfare measures is also something open and to be explored. So yeah, thank you. Any questions? I think it's time for coffee break. So yeah, could take it offline maybe. Yes. You want to announce?
Participative budgeting, it's so natural to look at the mix.
So we'll have a group photograph, let's say before lunch. So after the next session, hang around and we'll take a photograph and save it for our future generations.
Okay, welcome back everyone. So our next speaker is Aniket Murekar, who is a PhD student at UIUC, and he'll be talking about fair and efficient allocations of indivisible items.
Seems like the talk titles tend to get a bit repetitive, but I'm going to talk about different things. And I want to start by thanking the organizers of the workshop for having me here. So hopefully by now you're all convinced that resource allocation problems are really common. They model various real world settings, and to name a few things like division of inheritance, food distribution, chore distribution, task allocation can be modeled by fair division problems. And right off the bat, I want to make a distinction between these examples based on the nature of items that we're supposed to be dividing. So here the first three examples involve items which give agents a positive value to the agents receiving them. Whereas in the bottom three examples, they're chores. So agents receiving them get a negative value. And Ruta spoke about chores earlier today in the morning. Items here are indivisible as well. So here's the model. We have a set of n agents and a set of m items. Because they're indivisible, an allocation is a partition of the items into n bundles. Here xi denotes the bundle allocated to agent I. And agents express preferences over which items they'd like to receive using these valuation functions. So vi of s denotes the value that agent I has for the set S of items. And a common assumption throughout this talk is that valuation functions are additive. Okay, so what are fair allocations here? I'm also going to be considering the classical fairness notion of NV freeness, and its variants. So we say that an allocation X is NV free if for all pairs of agents I and K, the value that agent I gets from the bundle allocated to her, Vi of Xi, is at least the value she gets from the bundle of some other agent. And if you can say this kind of thing for every pair of agents, then the allocation is NV free. So in this example, Bob does not envy Alice, but Alice envies Bob, assuming that there are 5 goods which they equally like. Okay. So this example also actually shows us that envy-free allocations need not exist. And this is an example that's been repeated many times. So what is the natural relaxation that we can do? Alice can do this counterfactual thinking where she says that, okay, I may envy Bob, but after removing one good from Bob's bundle, her envy towards Bob disappears. Okay. So this motivates the definition of EF1, where we say an allocation X is EF1. If for every pair of agents I and K, there exists a good G that you can remove from K's bundle, after removing which the envy disappears. Okay. And the good thing is that EF1 allocations always exist. Okay. Now, in the case of chores, you can define EF1 similarly. But the thing to notice is that chores give you negative value. So Alice here is unhappy because she's doing 3 chores as compared to Bob. So she values her bundle less than Bob's bundle, but she can now remove a chore from her own bundle, and now after which her envy disappears. So again, for formally, we say that an allocation X is EF1 in the case of chores. If you can remove a bundle, if you can remove a chore from your own bundle, after which your envy disappears. Okay. So notice the distinction between goods and chores in further definition of EF. No, so I'm currently considering the valuations to be negative. So if you think of, instead of valuations, if you think of them as disutilities, which are positive, which capture the burden that an agent gets from an allocation, like Ruta had defined in her talk, then you're right, the inequality will reverse. So for chores as well, EF1 allocations always exist. So this is nice. This is good to know that we can get fair allocations. But fairness is not enough, right? So in this example, where Alice and Bob are doing some household chores and their disutility measures basically how much time they spend doing these chores, this allocation might be fair. But Alice and Bob can realize that, maybe they're doing tasks that they're not efficient at. So they can, Alice can say that she can get done with the cleaning in 1 hour and Bob can be done with the laundry in 1 hour. So if you swap, actually both of them are better off in terms of value, in terms of utility. So this motivates us to consider allocations that are Pareto optimal. So here formally an allocation X is Pareto optimal if there is no reallocation Y in which some agent is strictly better off and nobody is worse off. Okay, so I hope this
this is motivated you enough to consider fairness and efficiency simultaneously. So one can naturally ask the question, does there exist an EF1 plus PO allocation of goods? Can we compute it? And likewise for chores. And I've made a distinction between goods and chores here because what we know as answers to these problems is quite different. Okay. So these are the questions that I'll be touching upon in this talk. And my objectives here are to give you a kind of a survey of what is known for the F1 plus PO problem for goods and chores. And I want to give you a high level idea of what kind of ideas and techniques are used. And I want to talk about some open problems and directions of future work. Okay. So I'm going to start by talking about goods, and then I'll talk about chores, and then I'll conclude. So before I talk about goods, I think this is a good time to stop and ask if there are any clarifying questions. Okay. So let's look at these notions separately first. So let's look at EF1 and PO separately. So very simple algorithms like round robin or the NV cycle algorithm, which are like well known, well studied for a long time. These algorithms run in polynomial time and return EF1 allocations. So just to give you an example, the simple round robin algorithm in which agents are put on a line and they pick goods turn by turn. So Alice picks her favorite good in the first turn. Then Bob picks his favorite good among the set of remaining items. And they continue in this way, picking goods one by one. This round robin algorithm returns an EF1 allocation. But these algorithms need not guarantee allocations that are Pareto optimal. Okay, so what we can do is maybe you start with an EF1 allocation, you check if it's Pareto optimal, and if it's not, you try to improve it. But then doing this might make you lose the EF1 guarantee. And in fact, I'm getting ahead of myself here because it's not even easy to check if a given allocation is Pareto optimal. So what I want to emphasize here is that Pareto optimality is a really tricky property to achieve. So what worked for this problem, the first thing that worked for this problem was this remarkable result, which showed that the Nash welfare allocation, the allocation that maximizes the Nash welfare is both EF1 and PO. So this is great because it tells us that EF1 plus PO allocations exist for goods. But it's not very good in terms of computation, because it turns out that computing this maximum Nash welfare allocation is both NP hard and hard to approximate as well. And yesterday, Jugal spoke about a long line of work devoted to developing good approximation algorithms for this problem. But even having approximately maximum Nash welfare allocations, it's not clear if we get if those solutions retain EF1 or PO guarantees. Okay. So what worked for this problem in terms of computation was the idea of competitive equilibrium. And Ruta has already spoken about this today earlier in her talk. So, so in this Fisher market model, agents have budgets. So here Bob has $10. Goods are attached prices. So here the football is at $4 and the pizza is at $5. And every agent comes to the market with the aim of getting the maximum value they can get from these items by buying those items subject to their budget constraint. Okay, and here goods can be fractionally allocated. So to give you an example, Bob spends his $10 as $1 on the football, $5 on the pizza, and $4 on the T-shirt, and that's how he's spending his $10. So such an allocation X with a set of prices P is a competitive equilibrium if the market clears, which means that all the goods are sold and every agent gets their optimal bundle. So for additive utilities, what this translates to is that all the goods are sold, every agent spends all their budget, and most importantly, the allocation satisfies this maximum bang per buck condition, which means that if an agent I is spending any amount of money on an item J, on a good J, then that good better give him the maximum value for money, maximum return on investment, so to say. So Vij over Pj should be the maximum among all goods. This ratio should be the maximum among all goods if he's going to buy any of this good. Okay. So because of this MBB condition, Fisher markets are really useful in terms of giving efficiency guarantees. So for a competitive equilibrium X comma P, the allocation X is fractionally Pareto optimal. So it means that there is no fractional allocation which dominates this allocation. So it's a stronger property than Pareto optimality. Moreover, it tells us of a way to certify if an allocation is fractionally Pareto optimal or not. So if I tell you that here is an allocation and here is a set of prices which satisfy the MBB condition, then that's a way for me to certify that the allocation is indeed Pareto optimal. Okay. But markets give us more than this. So because of this MBB condition, you can express the value that an agent gets from her bundle in terms of the total spending of that agent. So here P of Xi denotes the total amount of money that the agent is spending, which in the indivisible case is simply the sum of prices of the goods that she gets. So if that happens, then this is essentially scale. Up to scaling, you can think of values in terms of money. And the MBB condition also tells you how to measure your value for somebody else's bundle in terms of the payment, in terms of the spending of the other agent's bundle. Okay. So if we are looking at NV-free allocations where you try to compare these two values, because of these inequalities, it suffices to compare P of Xi and P of Xk, which means you try to make everybody's spending roughly the same. And likewise, if you're looking at EF1 allocation, all you need to do is you need to compare the spending of agent bundles up to the removal of one good. So alpha is this MBB ratio here. So what is the takeaway? The takeaway is that it suffices to search for an integral competitive equilibrium x comma p that satisfies this price EF1 condition, which is the EF1 condition, but in terms of agent spendings instead of actual values. And this was the approach that Siddharth and Rohit developed in their paper, which gave us this good news, right? So for goods, EF1 plus PO allocations can be computed in pseudo polynomial time. Okay. But if you notice that you kind of lose this FPO guarantee here because there is some rounding that goes on in the algorithm. But later with Jugal, we were able to show that an EF1 plus FPO allocation of goods can be computed in pseudo polynomial time. And both these algorithms essentially use this approach of finding integral price EF1 competitive equilibria because that tells us that the allocation is EF1 plus PO. So although these algorithms are slightly different in terms of what they actually do, this is the main idea. And their analysis is different. But here I want to give you a taste of what the algorithm looks like. So let's run through an example. So remember that I want integral PF1 competitive equilibrium x comma p. So here my goal is to equalize the budget, the spendings of the agents. So I start with some initial allocation that looks like this. And the initial allocation should be welfare maximizing. So what I can simply do is I can take every good and assign it to an agent who likes it the most and set the price of that good to be the value of the agent to which it is assigned. So that will ensure that I get an initial integral allocation, which is a competitive equilibrium. So here, look at this graph. So the solid edges denote the assignment, denote the actual allocation, whereas the dotted edges indicate MBB edges. So for the green agent, the set of books is also an MBB. So it's also equally good, but it's just that in this allocation, he's not given that good. So our goal is to kind of equalize the spending of all these agents. Yeah, so the spending of an agent is simply the sum of the prices of the goods to which is assigned. So we are not looking at things like CEI, where the spending or income is fixed. For us, the budget is something flexible. We manipulate the prices, and then the spending of an agent is the sum of prices to the agent in that allocation. Okay. So here the green agent is kind of poor, and he is unhappy because he envies the rich agent who has $10. So here money is an indication of value. So if the green agent is not PF1 towards the red agent, then what you can do is you can make the red agent less rich by transferring an item along this MBB edge. So we only transfer goods along MBB edges because we want to maintain Pareto optimality. And the only way we know how to maintain Pareto optimality is by these supporting prices, is by maintaining this market equilibrium. Okay, so if you do this, there is some wealth redistribution. but now the green agent can envy the blue agent. Okay, so what you can do is you again look at some item and you transfer it. And in this example, the spendings are almost equalized, so you're done. Okay. Sorry, why will it terminate, right? Yeah, that's a good question. In fact, can we even do this is not clear yet, because so what we did so far is you started with an integral competitive equilibrium. You looked for these sort of alternating paths from the poorest agent, the least spender agent, to agents he or she envied, and then you made these transfers towards all agents which were reachable. But what if there are unreachable agents, right? So what if the situation is like this? So if the situation is like this, you want to make this agent poorer, but you can't transfer any of these goods away because there is no MBBH. So what you do is you look at this component of the least spender agent, and the component is the set of all reachable goods, and you raise the prices of all those goods. So what you're doing is you're making all these goods expensive. So these agents will feel like, okay, these goods are cheaper, so I will try to buy them instead. So you raise these prices until a new MBB edge appears from some agent inside the component to some good outside the component. After which you can do this transfer, right? But you're also making poorer agents richer, right? So it may happen that the allocation already becomes PEF. Or it might happen that there is a new agent who becomes a least. And the two algorithms that I spoke about treat these three events separately in a different way. But essentially, this is what they do. And once you're done with these price rises, you do some transfers and you continue this algorithm, and the hope is that this terminates. Okay, yeah. So the problem is that he does not envy this guy right now. So we don't want to break that envy. We only want to take care of like the problematic relationships. So right. Yeah, so you can break other envy relationships, but also the issue is that if this is an MBV edge, this item is cheaper. If you're making this $10, then you're making this expensive. So the allocation will not be on MBV, right? Because yeah. So if there is already an MBV edge, you don't break it. Yeah. It's no. I mean, it's not necessary, but it's sufficient. Yeah. Yeah. Okay. So this is the first breakthrough for this problem, which showed that there is an FP task for finding any F1 plus P allocation. So you round the VIJs to powers of 1 plus epsilon, and you get an allocation that's approximately F1 and FPO for the rounded instance. And when you round it back for small enough values of epsilon, the allocation is EF1 plus PO. Okay. What is the key insight here? There are many arguments that go into this work, which bound the number of transfers of goods as well. But the key insight is that this spending gap, which is the gap between the spending of the least spender agent and the spending up to one item of the richest agent, this gap decreases every so many steps, and that's why you get pseudo polynomial time convergence. What we do is slightly different. We raise the prices of all the least spender agent components together. And what we obtain is that because we don't do any rounding, we get EF1 plus fractional Pareto optimality in pseudo polynomial time. So the runtime of our algorithm is polynomial in N, M, and U, where U is the number of distinct utilities that any agent can get from all possible allocations. So you look at the set of all allocations, look at the utilities, and put them into a set. What is the size of that set? So the reason that we get this is because we prove that when an agent I stops being the least spender and becomes a least spender again in the run of the algorithm, then between these two events, her utility must have strictly increased. So how many times can this utility keep increasing? It can only increase U times. And that's why we get this runtime. So as a corollary, we get that EF1 plus FPO can be obtained in polynomial time for special classes like k-ary instances, where every agent has only k many values for the goods. Okay. So this is the picture for EF1 plus PO for goods. We also showed that you can do it in polynomial time for constant n. But more generally, it's open if we can compute EF1 plus FPO allocations in polynomial time. And the complexity of this problem is still open. So that's all I had to say about goods. Are there any questions so far? Okay, so now let's talk about something more challenging, which is the F1 plus PO problem for chores. So let's recall you have agents and you have these chores that you want to allocate. And we are looking for an EF1 allocation where for every pair of agents I and k, you should be able to remove a chore from your bundle, after which the NV disappears. Now, because I don't want to deal with negative values, I will look at disutilities instead, which are positive values. So Vij is a negative number, so minus of Vij is positive. So this changes the definition slightly, and there was a question about this already. So now we say that an allocation X is EF1 if for every pair of agents I and k, di of xi minus c is at most di of xk, which means like your burden after removing one chore is less than everybody else's burden. So we can try what we did for goods, right? But the first thing to know is that there's nothing like Nash welfare. So ideally, we would want a result like you minimize over all allocations some welfare function, and it turns out magically that that welfare function is EF1 and PO. So can we try just something like Nash welfare? If we try to minimize the product of disutilities. So the problem is that, of course, this is going to give 0 to one agent. So this is not going to work. Maybe we try to maximize it. What's the problem here is that you're maximizing the amount of disutility that agents get. So that's not going to be PO. And there are a number of things that you can try, which all seem sort of maybe intuitive initially, but none of them really work. And Siddharth was telling me yesterday that apparently there's a new result which shows that no such theorem of this sort is possible. Like there is no welfare function in the case of chores, which is both EF1 and PO. Okay. So then we can look at our second approach. Sorry. Is okay. Okay. So the second thing that you can try is to look at the competitive equilibrium approach. So the case of goods and chores is different. So here Bob comes into the market with the goal of earning some salary. So he has an earning requirement. He wants to earn $10, and he does so by doing these chores. So and again, his goal here is to earn his money by doing the least amount of work possible. Very sensible. So here is a possible allocation. Bob earns his $10 by walking the dog for $1, by reviewing a paper for $5, and so on. We don't get paid for reviewing papers, but just like that. So here agents want to earn their money subject to the least amount of disutility. So for additive valuations, what this means is that an allocation XP is a competitive equilibrium if all goods are done, if all chores are done, every agent earns their minimum salary, and everyone does chores that give minimum bang per buck to them. So the minimum pain per buck. So the disutility over payment should be the least. Okay. So because of this, the same efficiency properties essentially carry over from the essentially apply also to the chores case. So it's still a reasonable goal to look for integral payment EF1 competitive equilibria x comma p, where what is a payment EF1 allocation? You just say that P of xi minus c, the payment to an agent up to the removal of one chore, is at most the payment of anybody else. So one can really think of the standard algorithms that we have for goods for the case of chores. So let's look at an example. Suppose you start with an initial competitive equilibrium x comma p that is integral. The solid edges denote the allocation. The dotted edges denote the minimum pain per buck edges. So here, who is the agent who is worse off? So money really has no meaning for us. It's only a way for us to keep track of the disutilities to agents. So here the agent who is earning the most amount of money is actually the unhappiest because he or she is doing the most amount of work. So the richest agent actually envies the poorest agent. So the biggest earner envies the least earner. And one can try the same thing. You try to transfer some chores away from the big earner to the least earner. And maybe you do this, and so far things are okay. But what happens if there are if some chores are unreachable, right? So in this case, you cannot transfer any of these chores to the other two agents. So in this case, what can we do? We look at the component of the least earner agent again. What happens if we increase the payments of these chores? If we increase the payments, then these agents are happy. And these agents actually, the unhappy agents might start wanting to do these chores. But that creates MPBHs in the wrong direction. So what you actually have to do is you have to decrease the payments of these. So if you decrease these payments, these agents will be like, okay, these are high paying jobs, I want to do some of them, and then you get an MPBH too. Okay, so that's one thing to do. But here notice that you're making a poor agent poorer. The other thing to do is you look at the component of the big earner and you raise the payments of these chores. So if you're raising the payments of these chores are attractive, so these agents can start liking them and you can get an MPBH and you can continue your chore transfers. So again, we want to do chore transfers along MPBHs because that maintains Pareto optimum. Okay, so here we are making poor agents poorer. Here we are making rich agents richer. Okay, so the spending gap can really grow in these algorithms. So these can go down, or if you're making payment raises, these can go up. And that's one issue where I mean you can't really use previous potential function arguments, and there's no nice monotonicity here. That's the main situation. Yeah. That's the issue, yes. And there was this other analysis technique which looked at disutility of agents instead of like the utility of agents in the case of goods, where we showed that between instances where an agent stops being a least spender and becomes a least spender again, the utility has increased. But this kind of thing doesn't work in the case of chores as well. You can construct examples where between instances where the least earner agent changes and becomes the least earner again, the disutility can go up, can go down. It's not monotone. And so we don't have these convergence arguments, and well, if we did, then we would know that EF1 plus PO exists for chores, and we don't. Okay, so in the case of BADs, so far we don't have good news, but not all news is bad. We know that EF1 plus PO exists for these special cases. And the cases of identical valuations and two agents are kind of, it's easy to see why they exist. But the real non-trivial results for this problem for chores were for these special cases of bivalued instances, 3 agents, 2 types of agents, and 2 types of chores. And because I was involved in these projects with Jugal and John, I'm going to be focusing on them in the rest of the time that I have. Not for, yes, actually, you can get weighted EF1 plus PO by essentially using the same approach. So instead of looking at the EF1 condition, you look at the weighted PEF1 condition. So that works. Okay, so I'm going to tell you about these three results very briefly. And I want to start by telling you what are the key high-level common ideas in these algorithms. The goal is, again, to search for a PEF1 competitive equilibrium Cx, P, which is integral. And PEF1 here is payment EF. So the one thing we need to do is we really need to use the structural properties of the specialized instance class that we're looking at. So we can ask questions like, what do FPO allocations look like? What do MBB graphs look like? And we carefully have to modify the standard algorithm. It's not enough to just run this standard algorithm. We have to be very specific about what chore transfers we do, how we do payment raises, how we do payment drops. And then we have to ensure that it converges. So we want to somehow bound the number of chore transfers that you do using some different potential function. Okay, so let me start by talking about hard and easy chores, which is the case of bi-valued instances. So here Dij is between 1 and k. So the disutility that an agent has for a chore is either 1 or a larger number k. So it's either easy or a hard chore. So let's start with a initial allocation where everybody only does easy chores. So you can set their payments to be 1. And even this allocation might be, there might be payment EF1 NV in this allocation. So this agent is doing $3 worth of work. And even after the removal of one chore, he envies the poor agent. Okay. So what we can do is we can look at such an agent. We can raise the payment. We raise the payment exactly by k. And after doing that, we have these new raised payments. The agent is made richer. But in the case of bi-valued disutilities, the structure tells us that after you do such a payment raise, there is always MPB edges from the bottom agents to the top agents. So you can actually make a direct transfer of a chore from a big earner agent to a poor earner agent. So directly to the agent you are envying the most. Okay, and this bi-valued structure also ensures that there are two prices, and we can ensure that each agent undergoes payment raises only once. So essentially, there is a monotonic transfer of chores from the top to the bottom. And there is an asterisk here because that's not quite the case. There are really instances where we have to throw some chores back to the top. But basically, this is the idea. So there is this monotonicity of chore transfers from the top to the bottom, and that's facilitated by doing these payment raises. Okay. So next, I want to give you an idea about. I am still increasing the spending gap. Exactly. Exactly. So I'm still increasing the payment gap, but every agent undergoes payment raise at most once. So I'm not increasing this gap too many times. Moreover, after I increase the gap, I'm taking chores away from the top to the bottom. And this can always be done because these edges are present. Polynomial. Pareto optimality is polynomial time checkable for bi-valued. Fractional Pareto optimality you can do in polynomial time for any instance. But even for bi-valued, Nash, things like maximize Nash welfare, subject to the allocation being Pareto optimal, for the case of chores, still does not give EF. Doesn't even give prop one actually. So in some sense, yeah, this is kind of necessary. Yeah, you have FPO here, it doesn't matter. But I think even in the case of PO, it's exchange cycles. It's not exactly the same as binary. Yeah. We don't need it. It's better that you give your so what is the biggest envy, right? The richest agent's envy is the poorest agent. So it's nice that you can transfer directly to the poorest agent. Simplifies the. So actually, in the algorithm, we have many groups of agents in the initial allocation, and we raise these groups one by one. And there's this nice monotonicity that you go from top to bottom. Okay, so I want to talk next about 3 agents. So in the case of 3 agents, things are not so simple. But we start with one agent getting all the chores. And we set the payments according to his disutility. And what we do next is essentially we try to do monotonic transfer of chores from this first agent and to the bottom 2 agents. Okay. And to do these transfers, you need to maybe adjust the payments later on. And the main thing is that the top agent does not undergo any payment drops. The only agent who undergoes payment drops are the bottom two agents. So maybe you do some chore transfers and you get this allocation. The main thing to notice, the main thing that we try to maintain is that these two bottom agents are always PEF1 with respect to each other. No. So here, just for the way that we designed the algorithm, you drop the payments of these two agents. The top agent does not, the payments don't get changed. So we maintain that these two agents are PEF1 with respect to each other. And there is an asterisk here because that's not quite the case. It happens that it might happen because that you get a chore from the top and then the PEF1 condition gets violated. And then you need to fix this PEF1 condition. And so again, there's not enough time to talk about the entire algorithm, and there are like many subtleties involved. But essentially, the idea is to try to transfer chores from the top to the bottom. And you do these transfers in a very careful manner. Like you try to transfer from the top agent to the least earner directly. If that's not possible, then you check if you can do it to the middle earner under certain conditions and so on. But once again, the kind of main idea is to try to transfer chores in a monotonic way in some sense. The last thing that I want to talk about is this case where there are two types of agents. So the agents in the green box are all of the same type. They have the same disutility function. The agents in the blue box are of the same type. They have the same disutility function, but they might be different from each other. So here we start with one group getting all the chores, okay, and then you try to monotonically transfer chores from the top group to the bottom group. And here only the top group undergoes payment raises, and the bottom group does not. What we maintain here is that agents within a group are always payment EF1 with respect to each other. So there is no envy between agents here within this group, and there's no envy between agents in this group. So the only possible envy is from across these groups. And in fact, because you start with one group getting all the chores, the envy is from top to bottom. And we argue that if the envy reverses, then we must already be done. And the main, yes, that's what I mean by. There is like a clear direction in which item transfers are happening. It's a way for me to keep track of progress of the algorithm. So the sure, I guess. Yeah, maybe that's there is no space. Shrinking. That's it. There's no local like structure otherwise, right?
Once the application has been done, can you produce an order that justifies just item by item slip of the movement of the line?
Possibly. Yeah, sure. Okay. So I think the new idea here is to not commit to an allocation of the chores to agents in the group. It's like you maintain for a group a pool of chores that are allocated to that group, and allocation within a group is done using the round robin algorithm. So it seems like using round robin algorithm or NV cycle resolving algorithms along with this competitive equilibrium approach might give something for the EF1 plus PO problem. Okay, so to summarize, I spoke about EF1 plus PO for chores. Existence and polynomial time computation is known in special cases. And again, the main idea is to search for integral payment EF1 competitive equilibrium x comma p. And we want to use structural properties of the instance class, carefully modify the standard algorithm. And we need to think of different potential function arguments to prove termination. Okay. So I'm almost done. Are there any questions about chores here? Yes. EFX plus PO for doesn't exist actually. With 0 it doesn't. And it's hard to check, NP hard to check if it exists. But with positive, I'm not sure. like if non-zero. Yeah, but EFX plus FPO does not exist. So this won't help. Yeah, EFX right side. Okay, right. So what I told you about is the F1 plus PO problem for goods and chores. For goods, polynomial time computation is unknown. For chores, even existence is unknown. The general message is that bads are worse than goods, and we don't have a general approach yet. Okay. So what do we do if we are faced with this hard problem of EF1 plus PO for chores, right? So what we have been doing so far is to look at restrictions. You restrict the number of agents, you restrict the kind of valuation functions. And these are the next immediate open cases, like 4 agents, 2 array instances. And I think if we manage to solve any of them, they will give us like really good insights into what will work for the general problem. But there's another way to go about it. You can relax the problem. So if we can't get EF1, maybe look for approximate EF1. And nothing much is known for the problem for chores yet. You can also look at, if you can't get EF1, you can look at EF2, EF3, things like that, where you say that an allocation is EF2 if I can remove 2 chores from my bundle and my NV then goes away. The other direction, and this has been recently studied, is EF1 plus PO with charity or surplus. So, and then there are many other questions, like there was a question on weighted EF1 plus PO, EF1 plus PO for submodular, many such questions. So, yeah, EF1 plus, so how do you get EF2? Oh, that's EF11, right? So it gives you, I see. Yeah. So yeah, so that's all I had to say. Thanks for your time, and happy to answer questions. Via impressionism.
For sub-additive goods, we know that EF1 and PO does not exist.
Yes.
We check if the same people.
I have no. I don't know.
Either super or sub.
I think it's suborder is generally.
But EF1 definition changes.
Anything ordinary, like you can
When you remove it from your own bundle, I think that creates an issue.
yeah.
For chores, yeah.
I haven't checked it, but
So
I think
for monotone chores for EF1 and PO.
is known to not exist, right? But yeah, I don't think I don't know of a result for sub. I think linear in number of items might be known by rounding the Fisher market, but no dependence on, no constant is known for sure. No dependence on number of items is known, agents is known. And there are also results, so like prop 1 plus PO is known, but that doesn't give anything for approximate EF1. That doesn't give anything for EF2. That's okay. I think we know it doesn't exist. Zeros and
Yeah.
Yeah, okay. So I'm told that the photographer will come after lunch. So we'll do the photo then. Lunchtime.
Not exactly, we just see the schedule and which everyone's approaching. Be there. So click on new share when you want to switch to the presenter's laptop.
There's a photo we
You share
of everybody.
advanced
Downstairs for 5 minutes.
content from second camera.
Invite can come. Just go to 5 minutes later. Please come. We would like to have all of you.
That's it.
Come, please come.
And can you click on here? That's what it is.
It's not going to plan.
It's okay. It's too fast.
Yes,
मुझे मत पूछ। तो उसमें मतलब अभी मुझे पता नहीं डेट टाइम देखा है मुझे पता नहीं है स्पीकर को नहीं आना तो फिर तो ये है कि न्यू शेयर पे जाना है और यहाँ पे जो डिफॉल्ट है ये डिफॉल्ट ये तब करनी है जैसे टॉक एंड हो जाए इस पे जाना है और स्क्रीन करूँगा जो आइडियली हो जाना चाहिए ठीक है और जैसे ही टॉक स्टार्ट हो ये एडवांस और कंटेंट फ्रॉम सेकंड क्या था अब इसमें HDMI आउटपुट आ जाएगा
ये वाला
अब एक बार डिफॉल्ट स्लाइड
So there's just two things.
डिफॉल्ट साइड लगाओ.
Okay. Okay. And then the
Like-
other one is
Don't stop share.
those called,
हो गया.
and this one.
Yeah.
Which one?
HDMI. ये लगेगा ना.
But this doesn't go in all.
or you can just remove
Yes.
this and plug it directly.
This is HDMI.
Oh, understood. This we've used in class.
There are many of those USB-C microphones.
Hmm.
It's slightly different downstairs because we have this auto head here and there we have to manually do this high floating meeting control after you have done
Oh, I got
whatever.
it. If it's in the way, I'll just do that.
Yeah.
Hmm. So this won't like change the slide if I click.
No, even if it does,
But it doesn't.
if it's not going away then. And like I said,
Press escape.
Yeah. Cool. Thanks. Thank you. Like they'll tell you to change.
no, they won't. It's just if someone has any problems, they'll tell you because they'll see your yellow ID tag and yeah, okay.
What is the problems? For example.
So last one was there's someone I don't know if you probably heard it. I think you're that prepared.
What's stuff like?
Yeah, there's nothing any complex stuff.
Both of you will be on. I think I should. We'll have to go pick up. Okay. Thanks a lot.
Tomorrow conference. Tomorrow the conference starts, right? So I don't have to go.
Right.
Airport.
Oh, you want to see the conference?
Yeah,
Oh,
I paid for it.
okay.
Yeah, so probably should stay here.
Okay.
Start.
I'll stay with you. Or if you're okay.
I don't mind.
Yeah.
I'm fine with it.
Thanks, Arvind. Thanks a lot.
Yeah.
Bye. Wait, shouldn't they get intern?
Yeah, in the game.
Nice. So you finish your thesis?
Yeah.
Yes.
It was in electronics, but and now I'm more or less switching to.
Very good. Here we go.
So
Should I call it? The coffee.
Not from Nigeria that time. So something like that. So these kind of actions, the rate of it's like that you are there for the oh, great. That is actually it's very hard to characterize because
Okay, hi everybody, welcome back. So in the post-lunch session, so this is kind of an open session. So what I did was what we thought what might be a good thing is to ask some of the students who didn't have a chance otherwise to talk about their research, maybe talk about some open problems. So we'll have some brief presentations from some of the students. And after that, depending on time remaining, if anybody else wants to talk about open problems or just mention anything interesting going on in their lab or what they're doing, feel free to do that, right? So we'll start. So Varun from Triple IT is going to talk first about his research here. Just introduce yourself and then.
Presentation.
So that you can use PPT for the purpose. Present करना है, I guess. Clicker should be working. That's the only concern for me, which is not working.
लगा दिया?
No, that is not working. Some reason.
ऑन करना है उसको.
On है?
नहीं,
अच्छा,
off है.
तो tab
अभी
से भी आ
कौन
जाओ.
करना?
But yeah, so I'll be talking about fairness in transaction fee mechanisms, which is which is a problem we are trying to address. So Manisha, Sankarshan, Sujit sir, Rashid Parth, and I from Machine Learning Lab are involved in this problem. So I'll just briefly introduce the setting and then I'll move on to the open problems which are to be addressed. So transaction fee mechanism is a mechanism design problem in blockchains. So a blockchain has two components in its blocks, which is the block header, which is the metadata, and a set of transactions in each block. There are two types of players which we consider. One is a miner or proposer who proposes the next blocks to be added to the chain of blocks, and the user who proposes the transactions which are to be included in a particular block. So yeah, the transaction fee mechanism problem can be seen as a budgeted resource allocation. Because a block has finite memory, this can be viewed as a budget for the miner, and the goal is for users, for each user to bid some value to be given to the miner as transaction fee. And this, based on this auction, we can consider which transaction to select for the block. So resource allocation among users is done through transaction fee mechanism, which is represented by this tuple, where allocation, payment, and burning is happening. So I'll briefly talk about burning, which is not present in most auction settings. So allocation rule is defining which transaction are included among the set of transactions available to the miner. Payment is the payment that the user gives to the miner, and burning is the payment that the user makes, but it is not given to the miner. It's just that money is destroyed. So yeah. So in this setting, Rough Garden has defined the notion of myopic miner utility. Myopic because we are concerned only with one round where one block is being proposed. So here the miner's utility is given by the payment that he receives. And okay, so F is a set of transactions that the miner can include from his side to the block. So payment for miner from all the transactions from the mempool, which is for other users, minus the burnt amount from the transaction that miner introduces himself, and there is some negative payoff for using more size. So S is the size that is being used, and there is a negative payoff associated with using more size, which is where the budgeted constraints come in. So myopic miner incentive compatibility is defined when the utility maximizing strategy is that miner doesn't propose his own transactions to gain excessive payoff, and he follows the allocation rule X, which the TFM uses. User's utility is similar. So his valuation minus the payment he makes minus the money that is burnt. And for user, we use the DSIC notion of. So capital F is the set of transactions that miner is introducing in the block to gain excessive like payoff. So yeah, so yeah, so miner should not introduce fake transactions so that he can game the system. Yeah. So yeah, so those are the results of Rough Garden. First price and second price are not okay. First price is not DSIC. Second price is not minor IC. Yeah. Sorry. Yeah. So yeah. So Q is defined by the TFM. Okay, I'll discuss some burning rules here also. So beta burn FPA is some constant, like some fraction of the total bid is burnt, and 1 minus beta fraction is paid to the burn means it's not like it's taken away from the user and not given to the miner. It's just the money is destroyed, something like that. And we see that EIP 1559 is one transaction fee mechanism which is used in Ethereum, and it is MMIC and almost DSIC. So it can be made arbitrarily close to DSIC, but not exactly. So these are some results from the garden. And tipless is a trivial payment scheme where miner doesn't get anything, any payment, all the money is being burnt. So in that case, it is MMIC as well as DSIC, but it's a trivial TFM which is of no utility to us. So the problem of fairness in TFM is so if we introduce the idea of inclusivity of all types of transaction proposers, we would like to have two particular conditions. One is monotonicity, that is probability of a transaction getting accepted should be proportional to your bid or your valuation ideally. And zero fee inclusion, that is probability of a transaction with zero transaction fee should also be non-zero. That is, so this idea is motivated from UPI type of payment systems where users don't have to pay a transaction fees for making transactions, which has led to mass adoption of such a system. So that is where the motivation for
you're not offering transaction fees, or then your policy not getting accepted, is not the spirit of blockchain. There should be some non-zero probability that when you are not offering transaction, you should get accepted.
yeah, so there are multiple. Yeah, so
It's like ad auction where instead of displaying an ad, you're putting in it.
exactly. So
Yes.
the size is like block size is divided into slots which are being bid for by the users to include their transactions. So
Itself can masquerade as a
user. Exactly. So and also there is a scope of like side like off auction agreement between miners and users, so they can form a collusion so that the net utility of a collusion increases by deviating from the protocol. So I'll come to that also in a while. So based on these two, so are there any questions on the notion of fairness? If so the basic idea is monotonicity and zero fee inclusion. Zero fee inclusion for increasing the adoption of the system. So based on this, if we see, then none of the existing methods satisfy this notion of fairness, except tipless, which trivially satisfies it. So what we are trying to do is we are trying to come up with notions using either redistribution mechanisms or through randomization, like verifiable randomization, which satisfies all MMIC, DSIC, and fairness notions. So this is
To some
one.
extent some efficiency. Like, though it doesn't exactly fall under Maersk and Shuttleworth impossibility theorem, but it looks very similar because you have two sides of the market. You want IC and also efficiency. But there we have more technical conditions. Your valuations has to be continuous, same support and all those things, which is not here. But still, if you want to achieve efficiency, MMIC and DSIC, it still seems quite challenging problem. Or maybe because it has some connection with that Maersk and Shuttleworth impossibility theorem.
Yeah, so this notion of TFM was very recently generalized by, again, Roughgarden's group, because there can be scope for additional incentives through carefully ordering the transactions in a single block. For example, arbitrage or front running. So I'll just motivate through an example what each of these means. Arbitrage is basically exploiting the difference in values of some currency between two exchanges. So if there is market inefficiency, then you can have an arbitrage opportunity. And front running is if there's a transaction which will lead to fluctuation of prices in some exchange, then you can buy before that transaction and correspondingly have some positive payoff through that. So because of this, there is an added valuation to the block proposer or the miner. So for each transaction, there is some value, arbitrage value of the transaction, and for each subset of the block, subset of transactions of the block, there is some extracted value due to this subset of transactions, which is the front running or sandwich or other types of opportunities. So we'll try to abstract it into individual transaction based opportunities and a set of transaction based opportunities. So based on this modified utility for block proposers and the users, our goal, like one possible goal is to maximize the welfare, which is given by this equation, this sum of the valuation for the block proposer and the sum of valuation for each person whose transaction is included. So, but one very pessimistic result here is that for any TFM which is both block proposer incentive compatible and DSIC, the block that is proposed by the allocation rule, there always exists a better there always exists a block which maximizes the welfare better than this for any value of rho. So this means that for any non-trivial TFM cannot maximize the welfare. So that is the impossibility result. So this leads to the question that what is the direction of research if we cannot maximize welfare and if we cannot have IC. So there's another result which says that we cannot have both block proposer IC and DSIC simultaneously, except for non-trivial mechanisms. So if we cannot have both of them, then how does the TFM literature progress? So currently the setting is two auctions. This is again work by A16Z people, which is also Roughgarden's group. So it is basically the current setting is auction between three parties. One is a wallet service provider, which has a set of transactions, which they auction off to the builders who exploit arbitrage opportunities. And these builders then auction these blocks to the proposer who is going to add it to the blockchain. So this type of two auction setting is where the system is right now. And we have reasons to believe that this is inefficient or not fair. I think Rashid will demonstrate through an example how it is not fair. I'm audible. Yeah. So So why this happened in the first place, I'll explain. So what usually was happening in blockchains was, so there are set of transactions and they are sending their transactions, their intents to the miner. And the miner is basically the person like who is proposing the block. Now he is having the power to either censor the transactions, reorder the transactions and make money out of it. Like what Varul has said, arbitrage, for example, or let's say sandwiching. So you see a transaction, like let's say they are buying like huge amount of stocks and you know that the price going to like, high. So what you do is like you buy some stocks like, before you execute this transaction, and then you put like, this high valued transaction later, so that you earn like, a lot of money, because once the price goes high, so the 10 stocks that you bought, the price of each stock will go high. So there are attacks like this possible. And now the condition is there is only one miner who is actually in complete control. So what they have proposed is, so there is this team Flash Boys. So what they have proposed is, oh, we should not be having one miner, rather we'll split it into a proposer, a builder. The proposer is basically the miner who is going to publish the block, and the builders are the people who will be extracting the MEV, in the sense that they will be the people who will be ordering the transactions. So what happens now is there are two auction settings now. So one is the wallet service provider. So why do we have a wallet service provider is that, so not everybody can maintain a blockchain node. So if you are running Bitcoin, you cannot have a Bitcoin node like on your mobile installed, because it's heavy, storage heavy. So what you do, you tend to go for a wallet service provider, basically who is providing a service to you. You just log in and then you make transactions to it. So these are like, popular, and like we are going to see more like, of the users like, tending towards using wallet service providers. So you have a wallet service provider. So let's say you made a transaction. Now that transaction is put to bid like, among builders, people who are trying to make MEV out of it. So there is high value transactions with the wallet service provider, which are generated by the users. And now the builders are the people who will bid for these high value transactions. And then once they get it, they go ahead and they will bid for the proposer. So what they're saying is, hey, then we have some, set of transactions that we have put as a block, and we want to make money out of it. So in this particular round, can you please take our block and like, publish it? But the thing here is that the proposer will not have any access to the contents of the block that builders are prepared. So they will be only like, putting out their bids, and then the proposer selects the highest bid, and then we'll go ahead and the proposer, once it publishes the block header of the block which builder has created, the builder will publish the block to the network. That's what's going to happen. So no, builder will do it.
What happens is like proposers are like the miners. They already are specializing in mining. So what is generally proposed is, let's not worry about how to extract that maximum amount from these transactions. So different set of players will find out what are all transactions and how we can extract. So they are builders. So actual blocks will be written by proposers. Builders will just build a block and ask proposers or miners, why don't you write this block? So different builders will propose, build for it.
Builder, I can do the same thing.
Yes, you can do
But
it.
builder don't have that sophisticated hardware to mine the block. So they will find out arbitrage opportunities and they will propose, okay, why don't you write this block to the miner? So they are bidding to the miner.
The builder is seeing like some big companies buying 10 million stocks of this. Can you do that? You can wait for 10 minutes first, get it.
Yes, that is what builders will do. So we are not solving arbitrage issues. We are solving now because of this. So more value is created.
And
So how that value, extra value created by reordering transactions, it's shared across these different entities.
So previously everything was being like, sent to the proposer. He is getting the block reward. He is getting this extracted value. Everything is by him. So we thought, see, like some proposers might not be even like, have the hardware to even do this. So why not just split it into like, people who are actually interested in making this extra value, and like, proposer who is being selected by the protocol to publish the block. So the system changes to this, that user sends their intent, that is to execute the transaction, and then the wallet sends the transaction on their behalf to the builders, and the builders will push the block to the proposer and the block gets published. This is what is happening. So, but yeah, there are no bids and all. So considering that, so there are multiple wallet service provider. So users will be sending their intents to the wallets, and then the wallets will be doing auctions with multiple builders. And similarly, multiple builders will be like, bidding to proposer. So the proposer is the only single entity, rest we can have multiple entities like. So whoever wins the bid, like, gets the transaction from the wallet service provider, and whoever wins the bid with the proposer, they will be able to publish their block. Now, what is happening here is, so the wallet service provider is getting his bid from the top builder, and I mean the highest bidder. And similarly here in the proposer also, they are getting bids.
But we started looking in a different direction that like, is this even fair? That so why do we even question this is because see, there is this transaction that user is making. Wallet service provider, instead of sending it honestly to some proposer, what they're trying to do is they're trying to put it on an auction for a high value transaction that a user has created. So it's user's high value transaction that is being actually used by wallet service provider to make money. And similarly, builders who are trying to like extract MEV. So everybody is getting some or the other money, but then is it even fair that like the one who has created the value like from his money, basically he's the one who has created the value in the first place, but everybody is putting effort. So we thought, can we get like some kind of a notion like such that, or some way by which we can actually distribute the net value that they are generating. By net value I mean the high value transaction value, the MEV that the builder was able to generate, the block reward that proposer is getting. So all this money, the net value, can be redistributed back to the ecosystem so that everybody is able to get some money, but not like this. So what we thought was, what if we can figure out like, okay, in this particular round, there is this proposer, some set of builders and some set of wallet service providers. Let's say they have won this. So they actually got the block published with these people. So what if we can find how much each of them has contributed, like, in this, and redistribute the total MEV that has been generated back to these players? That was the idea. So what we are currently like, working on is using Shapley values to redistribute it. So how we are thinking of this is, so let's say like, a combination of wallet service providers, builders, or let's say, wallet service providers, builders, and proposer has published a block. We calculate the Shapley value of each of the user, like who in this, let's say, coalition, and then the net MEV value is redistributed back to each of the users based on the Shapley value. So this is an example, Parth will explain.
Hello, am I audible? So basically the wallet service provider, I have taken a This is better. So I have tried to highlight how the difference between an auction and a coalition can be highlighted in some distribution of profits. So I have considered a case where there are two builders, one wallet service provider and one proposer, and the value of the transaction VT is the amount of sandwich MEV that can be generated by the builder by bidding to the wallet service provider, and the value of that transaction is 120, let's say. And let's say the MEV extracted by builder 1, that is the arbitrage MEV, is 24, while the arbitrage MEV by builder 2 is 12. Then the auction setting proposer gets 12, while OFA gets 108 units of profit, because the profit that the builders are earning from OFA is being put into the PBS auction, the proposer builder separated auction. So it turns out that if builder 1 can steal the transaction BT from builder 2, then builder 2 doesn't have 122 put. So he only needs to bid a bit higher than 12, which is V2, builder 2 arbitrage MEV. That is why proposer gets only 12, while OFA gets 108. While according to Shapley value, I got this result that every proposer in auction, wallet service provider or OFA should get equal contribution, while the rest should also get some contribution. So there's a difference between OFA or wallet service providers fair share and proposers fair share that is not being properly met.
Yeah, so
Yeah, so they have tried to model it as a cooperative game, and then how Shapley value will divide this surplus among different agents, versus typically currently what is proposed is auction based. So auction based mechanism is actually proposer who is writing the block, who is the mining. is getting very, you can come to that example. So proposer is getting only 12, whereas Shapley value says that he should get 59 in this instance. So what is really fair division of this, whatever MEV is getting extracted? Whether Shapley value or some new notions are required? That is what like.
So
open-
basically,
Yes.
Yeah.
If I understood correctly, take the money back, generate the well, so generate for the user, but it was getting distributed among all the other agents. And you want to cycle it back, you want to give it back to the user or
redistribute to the entire ecosystem, like whoever has contributed for the transaction, the block proposer, and the block builder. So we want to redistribute the net MEP that they have created, the net value that they have created back to the ecosystem, so that it doesn't feel for a particular user, oh, if I'm not a builder, then I'm actually not earning a lot. A proposer should not feel that, hey, like I'm a proposer, but I'm actually not earning a lot. So, but everybody should feel whatever role I am in, I'm getting fair share of like, how much I'm contributing. That is.
right. So how do we capture that? How much I'm contributing?
That is the what open problem. Like
Yeah.
exactly how do you capture? One way we are thinking is Shapley value, but that need not be even perfect here.
I'll
So what is really fair division or what is fair contribution? That is what is bit open problem being proposed.
So basically, there is a flow of payment that is generated throughout the system to the to the wallet services, which is not fair because existence of builders is essential. Block proposer is also essential. So we want to distribute it equally among the multiple builders who are responsible for the block, as well as the multiple wallet service providers and proposer. Right. So yeah, where the unfairness comes is builders are competing for OFA and PBS. So they will overbid in OFA, anticipating their victory in PBS, due to which wallet service providers are getting more money than so they are due to their anticipation of PBA victory, they are overbidding in the OFA. So this value which is created here is transferred. So yeah, just to summarize, I think like the example is that the main question is TFM allocation rule fair as it is right now, and can we introduce a better notion of fairness? So the problem is that a notion of fairness itself is not defined here. So is Shapley value a good replacement because it also captures collusion among different players, and because a result of non-existence of IC, non-trivial IC mechanisms, can we have an approximate IC as well as fairness guarantees through some transaction fee mechanism? So these are the three major questions which the TFM literature faces currently. And other than this, there is a set of open questions posed by Elaine Shi in 22. So minor incentive compatibility, user incentive compatibility, and collision proofness among any C set of players. Is a dream TFM possible which satisfies all three properties? So her result is that it is not possible for deterministic protocols mechanisms, but can we use randomization? And if it is impossible in general, is the notion of incentive compatibility too strict? So does the IC notion needs relaxation? And the third question, which we have tried to address, is do cryptographic elements in blockchain? So outside of seeing this mechanism design problem from by using cryptographic toolkit, is it possible to circumvent the impossibilities and achieve IC and other properties such as fairness? So in one of our works, we have tried and achieved MIC, UIC, as well as fairness, although not collision proofness, but fairness, MIC, and UIC. So it seems that this is possible, but the more general question, like outside the context of TFMs and blockchains, is that is it possible to overcome other impossibility results in game theory using cryptographic primitives, such as verifiable randomness or multi-party computations? So is it possible to circumvent impossibilities through toolkits from outside. So yeah, so these are the questions we are addressing, and if there are any doubts, I'll be happy to answer. So right now the notions of IC are as stated here, but I'm not aware if contract theory based notions are both realistic in this setting and applicable. Yeah. So
There's a lot of connections there. And
the CSCP that LNC defines is C side contract proofness. So this like this notion of collusion proofness is sort of motivated from there, but it is open to like explore whether contract proofness based like IC definitions be helpful. So
how important is competence? Because Shapley value typically is hard to compute. It's a bit of approximation, but even then it's not an easy.
yeah, so one so if the answer to this question is yes, that fairness is a good alternative, then we will have to exploit the existing structures in blockchain to make assumptions on make assumptions and approximately estimate efficiently, because
So the thing is like, if you don't include transaction creator, is not going to be a big problem, because typically number of builders and OFA or for one block, there is only one proposer. No, OFA also few service providers, so it's not going to be a problem. But once we start including transaction creators, then it will be a big problem, because transaction creators will be little bit large in number.
Just to put a number, there are 1,000 transactions accepted through one block in every 7 minutes. So computation is going to be a challenge.
But if you keep them aside, then just hardly 10 players. So not a problem.
Yeah. So
yeah. Am I audible? Yeah. So good afternoon, everyone. My name is Pranoy, and I work with Sujit sir also. I am constantly guided by my senior Sambhav sir, who is not present here, but he guided me in this presentation overnight. So I just wanted to tell you all about what I do. So I work on federated learning settings. So I'm trying to include multi-arm bandits problem in federated learning settings. So just to give a brief overview, I will start with MAB, then I will mention what are the current state-of-the-art works for fairness. Then the related works will mention the fairness works in MAB that are currently existing. Then we will move to introducing the term of fairness in federated learning settings and how can we use it. So this is where the open-ended problem starts. How can we precisely define the fairness terms in federated learning settings, and how can we include that fairness constraint in multiple examples? So there I try to give an example just to explain how can we introduce that fairness notion, and then I summarize it quickly. So the multi-arm mandate problem is a very important algorithm that we use in real world applications in a lot of instances. So we try to model the agents as the multi-armed and arms in that MAB settings. And then we try to learn certain parameters of those agents in these MAB settings. So some of the most important example is crowdsourcing. So where we have a requester where I just basically want some work to get done. which makes me learn that if I do collaborative learning, then collaborative learning will help me to learn that things faster. But also then we have to look at the privacy constraints, because if I don't look at the privacy part, then collaborations will happen, but the privacy would not be there. So we need to make sure that privacy preserving is an important factor in that collaborations. So that would be done when we don't share any personal informations. So this kind of settings is what federated learning systems talk about. And that is where the federated bandits would come into play. The second is the recommender system example, where we have some K arms. So we can treat these K sets of agents that we can have, and we can treat them as arms and then train that model by some local servers, which would be the agents. And then we can give personalized recommendations using this global popularity. So using this global popularity. The third is the cognitive radio. So basically what it says is that there is a base station which wants to know which particular channel among these, like this is one channel, this is one channel, these are separate channels, and this is whole coverage area. So the base station wants to know which channel can I use that is not currently occupied by most of the coverage areas. So it tries to learn it using a federated learning settings by understanding these K-arms in a multi-arm bandit settings. So these are some basic examples where multi-arm bandits can be used in a federated setting. So the current multi-arm settings works on winner's take it all algorithm. We have a best arm, which is pull O of t times, and suboptimal arm, which is of O of log t times. But the notion of fairness is not yet included in this normal multi-arm bandit settings. So there are some works that I would like to mention. The first work is fairness of exposure in stochastic bandits. So this was the first work where this fairness of exposure was introduced. I have very less time, so I will just quickly go through it. So we wanted to introduce the notion of fairness because in the conventional bandit problems, there was no notions of fairness. So to introduce the notion of fairness, the authors propose here the FairX UCB algorithm, where they try to use the exposure notion to incorporate fairness in it. So this is the normal stochastic MAB settings, where we always try to maximize the expected reward, cumulative expected rewards, which is just this expression. So the issue is that if we include this conventional settings here, then what happens is that conventional bandit algorithms tend to always learn the arm which deterministically selects the largest expected reward. But what we want is the desired policy to include fairness as well. So there we try to incorporate this fairness constraints, where we try to define this ratio where pi star is the policy that we want to learn. That policy, which means that it is a fair policy. So we want this ratio to be equalized over all the arms that we have. So using this, the authors propose this theorem where if we define this policy as this, where f is basically a merit-based functions. This f is greater than 0. So we basically try to define this merit-based function of a particular arm with respect to it divided by the summation over all the arms. So if we define regret across the t rounds in this way, which is basically the optimal minus the suboptimal, and similarly for the fairness regret. Okay. So these are the assumptions that it requires. So this is basically mentioning that we can do it in root kt times, which is sublinear, which is obviously the thing that we always want to happen. So these are, and similarly, this is another paper which is mentioned by Ganesh. Here also they have tried to address fairness in multi-arm bandit settings. So here they propose this fair learn algorithms where they treat fairness, where they have two parameters, unfairness tolerance, and the learning algorithm is treated as a black box here. So they prove that the fair learn satisfies the fairness constraint at any time step t. So they try to incorporate fairness at every round of their multi-arm bandit settings. So fairness guarantee for fair learn algorithm holds uniformly over time and independent of the learning algorithm chosen. So these were the major contributions by Ganesha's paper. Moving on to the most important part, which is including fairness in the federated learning settings. So I envision to incorporate fairness in FL settings. So in FL settings, we have different clients, and the different clients are building models, and the server is aggregating them. So the server then sends them back, the clients then build the models, and then the server is aggregating. So this keeps going on and on. So now we want to model clients as the arms of bandit algorithms so that we can use it in the applications of the MAB settings. And then we can ensure fairness in it. Now, ensuring fairness is not trivial. So it is a very non-trivial problem where I have to ensure fairness not only at the client's level, but also at the model levels. So the two key points that I want to what I want to make you note is that unfairness in client selection may include model biases. And identifying clients which are offering better fairness accuracy trade-off is also important. So these 2 points I would like to explain from the following example. So if I'm using, so basically I'm trying to explain if I have a bias induction in FL models, then how can I use a fairer client selection method? So let's take the example of this hospital settings where I have multiple hospitals and I want to train an algorithm here. So in this FL model, the clients could be clinics or hospitals. These are my clients in this federated learning settings. Now I want their data to train the model, but I don't want them to share the data. And that is why the FL settings comes into play. But the data in the clients, so let's say this client is a well-funded clinic, so it will have access to more high quality data. So I tend to give this setting more weight because I know that this client would have better data. And this would result in my model optimization. But I'm not sure if that system would lead to fair FL settings because it can induce biases in my model as well. Because as this is well funded, then it can incorporate socioeconomic based or race based unfairness in my aggregated model in the server here. So this federated learning settings involves fairness not only at the client level, but also in the level of the server where we are trying to aggregate it. So this is a paper, survey paper, which is fairness and privacy in federated learning and other applications in healthcare, which tries to incorporate all the fairness terms in the FL settings. The state of the art was mentioned in 2023. So it mentions notable works. So 3 approaches that I would like to quickly mention here. The first one is client selection. So client selection, as I just said, is a very important task. Which clients do I select in my FL settings is a very important task. So nodes are allowed into the framework based on their potentials according to their contribution evaluations. So I mostly try to select those nodes which have the higher tendency to lead to an improved global model. But that can lead to unfairness, which we are never try to relate in our FL settings. So we can work on client selections, fairness, including fairness in client selection methods. Then we can look at incentive mechanisms. So in incentive mechanisms, the federated learning system distributes the rewards, which can be monetary, to clients in a standardized manner. But this does not indicate the vast differences that clients node may have in terms of local computational and physical resources. So particularly if I am participating in it, then just because of that participation, it cannot ensure that I am having this standardized distribution of rewards. So it will lead to free rider problem, and we have to prevent, and it will prevent high quality contributions from being represented. So we can incorporate fairness in these incentivizing mechanisms as well to have a fair federated learning settings. And the third broad area of fairness in FL settings is model optimizations. So here what we try to do is we try to make changes in the algorithm itself. So what changes can we make to the algorithm to introduce fairness in the framework? So I can adjust the weight or add some additional fairness parameters while aggregating at the server level or something like that. That will help me to make our federated learning systems more fairer. So So that is the things that in FL settings we can improve fairness. So this is the modern area of research. So these are the broad mechanisms that are currently proposed, but it is an open problem. We can all talk on it anytime. So that will be it.
Hello all, welcome back to Fair and Efficient Division of Goods again. So
Sujit Pujar. He's from IIIT Hyderabad, and he'll be presenting fair and efficient resource allocation using neural networks. So over to you.
Hello? Am I audible at the back? I'll start. Yeah, I should thank Siddharth and Umang for involving in this workshop. I'm a little bit outside this community. I'm not too much into really what the fair and efficient allocation and so many algorithm complexity results. I'm not really into that. So when Umang and these guys asked me, even can you present, I was a bit not sure, but then I thought, okay, let's. So we have addressed some of these issues through different perspective. One is again, little bit theoretical side. One is very completely different. So I will give more overview of neural network and then what we have done other bit theoretical side. So I don't have much algorithmic experience, so I won't be presenting many algorithms. So I'm more for like game theory and incentive engineering background and multi-agent systems. So I look at the systems, little bit system side, but I say myself I'm theory for AI rather than complete theory. So as we know that AI has been affecting our lives and getting infused our life quite heavily. Autonomous driving, robotics, ChatGPT, computer vision, and even many AI-assisted decision-making tools are getting developed, like Compass in US for jurisdiction, then crowdsourcing, crowdfunding, some of the work Manisha and others present are crowdfunding, online advertisement. So many places AI is getting used. So I will focus on resource allocation because that is what this workshop is about. I won't get into this. Everybody know what is resource allocation, so I will skip this slide. So typically when we talk about fair division, we want the resources or items, it could be goods, chores, or combinations, to be distributed among all agents fairly and efficiently. And people have come up with different fairness notions. NV-free, proportionality, EFX, EF1, equitability, MMS. NV-free means like no agents enrich each other. So you could construct examples how NV-free could be achieved, but we all know that it's not always possible to achieve NV-free. Like suppose this is example, this is one vaccination dose available on 3 contenders. So she is healthy. They are elderly couple who stays next to her, and on the other side, this girl is sick. Only one vaccination dose is available, and who should get it? And whoever gets it, others will envy. I'll come back to this example later. It has many interesting directions. So as envy-free do not exist, like that example or the famous diamond, so you cannot split the diamond, that example, indivisible goods, envy-free did not exist. So EFX and EF1 are well studied. So EF1 says that if you remove one good, there exists at least one good from other the envied agent. Like I'm envying certain agent, and if you remove one good, there is at least one good which if I remove, I will not envy him or her. So such allocation is called envy-free up to one goods, EF1. Like for example, this instance, there are 2 agents, 3 goods. EF allocation do not exist, but the circle one, like if agent 1 gets this tree and book, and this agent 2 gets 6 for car, then it's EF1. Because if you remove this book from his allocation, so this tree from his allocation, he will not envy his agent 1's allocation. And the agent 1 anyway is not envying agent 2. So EF1 Again, existence is a bit challenge, you all know, but general monotone allocations, valuations, we know that it exists and you can compute it in polynomial time. For efficiency, Pareto optimality, Nash social welfare or like utilitarian welfare have been talked about. And if your valuations are additive, simplest case, finding MUW, like maximizing utilitarian welfare or social welfare, is very easy. It's polynomial time and it's very easy. So now we're wondering, can we get, because if you are looking for fairness, you have to compromise on efficiency, MUW. So now amongst all possible allocations, suppose we are under additive valuation, amongst all possible allocations, which are EF1, which will maximize my social welfare. We call such allocations as EF1, efficient at EF1. And such allocations are NP hard. That was proved by Aziz et al. In 19. Even when there are two agents and additive valuations, they come up with some algorithm which is exponential in terms of number of agents. And another problem which we are considering, like this, where EF do not exist. Suppose I am this healthy person, I don't get this vaccination dose. If I get it, I have some valuation, but suppose I don't get it. If other two people who are neighbors to me, they get it, their health will improve. So because of which, my chances of getting affected by such disease from these people will reduce. So I still have certain valuation for this. Whereas this little girl, if she doesn't get it, so typically we say valuation, if you get the object, we have some valuation. If you don't get it, we assign it 0. But right now she is a bit critical to get this vaccination. So if she doesn't get it, she assigns some negative value to this. And now how do you calculate or define fairness? Do existing definition generalize in such settings? So we call such as externality. So she has positive externality on this allocation where she has negative externality. So there are the two problems which we have addressed. And this has resulted into 2 papers. The first one about how do you get EF1 allocations through neural network, and other is about these externalities. So externalities was also best paper award at Precare. But I will focus more on this because I thought anyway, this community already knows a lot of algorithmic results. So let's look at little bit different perspective and what insights it is offering for fairness. So there are the key results. So when we started working on this in 21, so maybe literature has more results available for efficiency and fairness. But primarily, EF1s are very hard. So the way we looked at it, like say you have valuation space, you want to find out allocation, that is given input, the different agents valuations, you want some allocation of these resources. It could be goods or chores. And typically people ask questions like, does F exist with certain properties? Like, does there exist F which will guarantee that allocations are envy free? Answer is no. EFX, we don't know. EF1, very general valuations of like monotone valuation exist. Proportionality, MMS, there are different questions people have asked. And then algorithmic challenges, like can we compute if it exists? Can we compute in polynomial time? If not, can we find out approximations in polynomial time? So we want to consider this as a function from valuation space to allocation. Can we compute this EF1 allocation? And our approach is a little different, like all due respect to the community which look at theoretical complexity, which has a lot of importance, like complexity results and all those things. But many times this worst cases may not occur that frequently. Like Hamiltonian cycle is NP hard, but many times you can find out very quickly. Market equilibria. Market typically we observe at equilibrium. So worst cases may not be that frequently. So as a practitioner, do we have to really worry about all these results? What if I say that I'm happy with some F, which is efficient to compute, and with high probability, allocation is EF1. and achieves at least beta fraction of my welfare. Can we have such Fs which can be computed quickly? And again, I'm not too much algorithmic person, so I don't want to do myself. Can machine do it for me? So can machine learn such F for us? Primarily through neural networks. And what motivated us for neural network is, like David Parks started this optimal auctions in game theory are a bit challenging, and he proposed neural network can learn for us. So we thought, can we do this through neural network? And there are a few other works like in coding theory, they showed that neural networks can learn Viterbi algorithm. So neural networks can learn algorithm because these algorithms can be treated as a functions, and neural networks can learn it. So now we don't know approximation algorithm for EF1. At least when we started, I don't think there was any algorithm available. Right now, I'm not sure whether there are approximation algorithms for additive evaluations, but at least that time there was no available algorithm, approximation algorithm polynomial type. So can neural network learn this for us? And another like challenge we faced while publishing this is some people are started objecting because now you are working not worst cases. So there was this paper in IIII 14, which talks about, the title is interesting, the computational rise and fall of fairness. I think again it's on right side. Maybe 14, there was a time where fairness was little, papers were going down, number of papers. What they showed is, if you have a large number of goods, n number of agents, then m at least n log n, and your valuations are additive, and they are distributed uniformly. All agents value between say 0 to 1 all the goods, and they are sampled from uniform distribution. We know that typically indivisible goods EF allocation did not exist, but they showed that such cases EF allocation exists with high probability. That as m increases, the probability increases, and at m tends to infinity, you will get that probability of EF allocation existing to be 1. And that their more motivation was to look at the existence. But in that pursuit, they were also interestingly observed. Yes? No. No. So what they showed, their analysis was more probabilistic, like does this exist? Not finding, but what they observed, or what they could also prove, that if you just maximize social welfare, and you have a large number of goods, typically that allocation itself will be EF. That is what they. So when we started writing this paper, some reviewers asked, anyway, because of this result, you are taking uniform valuations or some variations of this. It's bound to exist, so your neural networks are finding. But what our experiment suggested, this omega absorb large constants. Well, I think there is typo here, constants. So even if there are 12, 15 agents, and you have about EF, if you have around less than 100 goods, MUW allocation being EF1 is less than 0.5. Means M has to be really very large. Even our experiment suggests that if you take M to be around 500, it goes around 0.6. EF, sorry, EF1 you will get, but MUW allocation being EF will not be very high. It really needs M to be very large. Which one? What? This is the title of the paper, IIII paper. Yeah, this probabilistic analysis, this theoretical. They show that if you do MUW, then with high probability as omega is n log n, then you get this. Yeah. Yeah. See, if n and m are very small, even if you don't have to worry about complexity result, your integer programs will quickly find it out. M is very large, maybe we can do this MEW with this result, we are done. We can get EF1. But when M is not really very large, but not small enough to do it as an integer program, what to do? So we proposed neural network approach. So typically n is equal to 10, 12, and m is equal to 15, 20. It was working fine. We didn't experiment too much to see when it stops working. Yeah, so many times it will give, but there will be few instances that these programs will not quickly find it out. So our contributions are, we propose neural network, which we call EF1NN, to find out EF1 allocations. The architecture is inspired by UNet in computer vision. We do some transformation on your valuations and do some augmentation, and all the details are in the paper. And the series of convolutional network, and we did a lot of experiments. Our observation is that after training, it takes a couple of hours, not too much training. After a couple of hours of training, our neural network outputs with probability greater than 0.99 EF1 allocation, and it achieves at least 99% of MEW allocation welfare, because we don't want to, there is no polynomial time algorithm to find out EF1 allocation. So what welfare will be achieved, we don't know, but that has to be less than MEW. But we observed that it achieves at least 99% of MEWs. That means even it is achieving at least 99% of EF1. Yes? Yeah. Yeah. No, we haven't looked at theoretical aspects. So that is the questions for theoretical community, that will this be really generalized? So we trained it for only specific values of M and N. And our experiment suggested that it is learning for large number of N and M combinations, though we don't train for them. But we haven't done theoretical analysis. Or will it generalize what is really guaranteed? These are all experimental guarantees. Like we generated 20,000 instances, I think 20,000 or 2 lakh instances, and really checked them. And 99% of them were. So because of large number of instances we have tested, we believe this is true, but there are no theoretical guarantees. Yes, there are challenges in training. Yes.
So the training data itself will be random?
Yeah, random instances. But the beauty is in couple of hours, we are able to get this kind of results. Means couple of hours of training, but months of finding out how we should train. And there are many theoretical open challenges, like he's asked. No, yeah, that is also another interesting thing. So somehow for this problem, UNet has worked. Like there are some people have started work, can neural networks solve integer programs? And they are using graphical neural networks that are very training-wise computationally very intensive. Whereas these UNets are not easy. So for this particular problem, UNets are working. That is what our observation is. You don't need to go to graphical neural networks. But we don't have any theoretical guarantees like what Rohit is asking, VC dimension, all those things. We haven't looked at it. Another interesting thing in our experiment, whatever M and M we tested, our neural network is fixed size and it doesn't have, so it takes N and M as the input. But otherwise, everything is independent of N and M, main neural network. And we are seeing that at least all experiments, we are getting good results independent of N and M. Our training is independent of N and M. So why neural networks are able to learn? So we are parsing all N cross M inputs have to be parsed. Is the additive evaluation. Still, you need N cross M inputs. They have to be parsed, and then so that parsing is depend on N and M. But after parsing, neural network is independent of N and M. So why that is happening? So even finding out such fairness and efficient allocations is that valuation, understanding valuation is only important. After that, finding out such things, are they easy? Is one interesting theoretical question. I think one should look at it. No, that we haven't done. So we generated with different distributions and validated, but not on real data. At least our experiment didn't say that anything is really difficult or easy. They're almost all distributions we are able to learn very quickly. We didn't find the para alpha beta changing much. We tried Gaussian, direct, and uniform. Any other distribution we tried? Only these three, right? Yeah. Yes. Yeah, between 0 to 1. Let's say between 0 to 1. Yeah. That I don't think will matter much. As long as they are uniform between some range, that should not matter. And one more thing which I forgot to put on this slide, which maybe I will talk. So basically what we are trying to solve is this optimization problem. Instead of worst case, expected case, we want to maximize social welfare, minimize minus of that, subject to. Yeah, actually we want to do EF1 constraints. But again, our experiment, so what happens is in neural network, you don't put this constraint directly, you put them in loss function using Lagrangian multiplier method. So you weigh them, and this will not be always 0. Loss will try to minimize, but it will not be 0. So if we put EF1 constraint, somehow we observed that in training that it was not really getting EF1 allocation after we have trained the neural network. After it has converted to some local optima, it was not getting EF1 allocation. But we put these constraints as EF constraint and train the neural network. So that means we will minimize the loss function, this plus lambda times this. And if we put EF constraint, the allocation is not NV free, whatever we are learned, but allocation with high probability is EF1. And also one more observation we made is like Lagrangian multiplier method. So you have to weight this by different, like some lambda. So we tried with different lambda. And no one lambda particular was giving really good result. So what we did is like train for different certain instances. Some lambdas were doing better, on some other instances, other lambda were doing better. So we backed these neural networks using different lambda values. And that started giving us good results. So maybe there are certain valuations where this has to be weighted more, and certain valuation profiles where this has to be weighted more to get EF1 allocation. So that is also interesting direction one should explore. That why different lambdas are in different range doing good results. But so you want overall good result, we just have to back. But why different lambdas are performing well in different regions of valuation space. So this is our architecture. So it is like convolutional neural network mutated from unit. So input parsing happens, like you keep reducing n cross m to some fixed size. And then you do a lot of series of convolutional neural network. And in the end, you have to do softmax. No, neural network output will be real numbers. So as Siddharth was asking, yes, because our allocation, we want integral allocation. And neural network tend to learn. Initially, we observed that divide all atoms equally amongst all agents. That is like sort of, you can say, in uniform valuation is global optimum. But we don't want to do that. In neural network training, typically what happens is this softmax has this temperature parameter. So you weigh different output, and then this is a probability with which you allocate this good to this agent. And T, typically in general in neural network classification, whatever it is, initially is very high, and you slowly reduce as training goes on to T is equal to 1. So our initial approach, which also worked, but it was not really sounding very technical. We start with high T, reduce it, then again go to high T, reduce it, like sort of sawtooth. But we didn't have any real clear idea why it is working. So typically T is greater than 1 many times. If T is very high, then you are almost giving equal importance to 1. But if T reduces, then you start getting discrete allocations, but then you may face a problem of vanishing gradients. So you cannot make T arbitrarily small. So if T is closer to 0, this will definitely give discrete valuations. T is high, you are getting uniformly splitting across all agents. So we fine-tuned by experiments and we observed T is equal to 0.01 gives good result, which are better than our initial experiment of sawtooth kind of T values. And like different lambda values, Lagrangian multipliers, we are getting different equilibria, sort of different optima. So we have to back. So that means different lambda values or identifying good EF1 allocation only certain particular region of valuation space. And we did different ablation studies to validate that, yes, we are really doing optimal. These are some of our experimental results. So alpha indicates probability that allocation being EF1, and beta indicates what fraction of social welfare it is achieving. So if you look at MEW for 10 agents and number of goods starts increasing, probability of that being EF1 increases, but is still below 0.5. Whereas our neural network, at even at 50, it's closer more 0.8, and as it increases, it very quickly reaches 1, almost 1, 0.99. Whereas round robin or this cyclic round robin by Harris, they will give EF1 allocation. So their probability of being is 1. Whereas if you compare social welfare, no, so MEW will give maximum social welfare, whereas ours is quite high. Whereas if you look at the round robin or cyclic round robin, they're getting quite closer to MEW, you need really large number of goods. But whereas our neural network is getting quite good social welfare, able to extract it. And same neural network we use for chores. And now here is to be, you want lesser the better. So we observe that we are very close to 1, whereas round robin, it's initially quite bad. And we also studied for combination of goods and chores. And again, that setting also, we observed that neural network is performing quite well. Again, we varying number of agents also we tested. Same observations. Different distribution we tried. Gaussian, log normal, exponential. So all settings we observed that neural network is able to learn quite well. The Dickerson and their AAA paper only talked about uniform distribution, but we observed that even other distributions, probably that it's highly likely that we get this. One more observation we made is the neural network, which is finding, so say number of goods is 500. But whatever outcome neural network is giving, probability of that being EF, it's around 0.6. But probability of that being EFX is around 0.98. So there is existence question on EFX. So maybe possibility that EFX may exist for if you have large number of goods. I'm not sure, just our observation that whatever neural network is giving outcome, we observed that for large number of goods, like M is equal to 500, with probability 98, it is getting allocation, which is also satisfying EFX. So there is a high possibility that most on the instances EFX will exist. Yeah. Yeah. But that is asymptotic. And we don't know really how big numbers are required. Whereas 500, we are getting EFX with a high probability, but at least neural network output. Maybe MEW output, I don't think we tested for that good. But neural network output was not EF. So we put that as a constant. Lagrangian loss function has EF constant, not EFX or EF1. But again, neural network will not really optimize to 0. It will try to get closer to 0. But that neural network is learning EFX. So to conclude this part, we have proposed a neural network approach to find out EF1 allocations, and we are able to get with probability 0.99, achieving at least 99% of the social welfare on additive valuation. Again, these are all additive valuations where this problem is inferred to extract EF1. And we have done a lot of experiments to validate this idea. It's not just one set of experiment. So we believe that such deep learning based resource allocation can provide more insights into this realm of a lot of theoretical results or possibilities, impossibilities, and open problems. So we believe that such deep learning based approaches will definitely give more insights, and they will be practically very useful in many settings because worst cases may not occur frequently. Any questions on this part? Otherwise, I'll move to other part. Yes. Yeah, good question, but we haven't done that. We assume independent. Yes. Not too many. I think some 10 cross, 20 cross, something. You remember exact sizes, Manisha? Not really huge network, and it takes only a couple of hours to train. Yeah, that is like a lot of things can be done now. Like a lot of things can be experimented. Like look at what are the better representations, and even that ablation studies we have done that different lambdas are giving on different valuations. So many interesting challenges need to be addressed further here.
I think even round robin starts in
Yeah, after large number of goods, yes, round robin and MUW, the MUW is better, right?
starting.
Yeah. So but for neural network, you just initialize randomly, train it, and just give input and find out what is the output. So I'm not sure whether how easy it will be to start with allocation, which itself is round robin output. That may be interesting direction to explore. Can we train a neural network with allocation as the input also? So right now, allocation is not input, just valuation is input. That is also another interesting question. Yeah. Yeah, so like as compared to many other integer programs, people have tried using neural networks. This is much smaller. Not 100 agents, but we have tested up to 15 agents. But while training, we didn't use different N and M.
Right. So it's not this overfit.
Yeah. It's definitely not overfitting, but yes, the results are good on the N and M we tested. But suppose we started testing 100 agents and thousands of goods, we are not at this point sure whether this will really get similar results. But we believe might get. But then our neural network size is independent of N and M. So then why? Just representation is important or what? That is one interesting question I think one should address. Any other questions? How much time I have? Okay, I will quickly wrap. This is a bit easy side. Just interesting insights you can take and then look into. So as I told you that example, there are allocation may have externalities. It's not just I get it, then I have V, otherwise 0. So how to achieve fairness and in such externalities? Again, I'm not being algorithmic person. Instead of designing new algorithms, can I leverage existing algorithms? That is my goal. So in general, it becomes quite challenging. So what we looked at is special externality, which we call as sometimes valuation as 2D. Yeah, this is a valuation space that if I get allocation, some good, I have valuation VI for good K. And if I don't get it, it's VIK prime, which we address is negative. That is called negative externality. And like suppose I get this tree, I have valuation 5. If I don't get it, I assign it to be -20. If I get car, I assign valuation 6. If I don't get it, -20. Similarly, agent 2. So now we can define our net utility to be whatever my allocation, and sorry, this should be prime here. Whatever I don't get it, what is that externality on me? So one may feel that we can work with utilities, but somehow we directly, so traditionally we don't have to worry. Utilities and valuations we interchangeably use because this term becomes 0. But here we have to work with utilities. So we show that proportionality cannot be very easily just adopted in new setting. So we little bit need to change the definition. But whereas EF, EF1, those can be adopted. So we call it proportionality with externality. Then how we can reduce the problem from 2D to 1D? Yes? Yeah. So because 1D we have plethora of algorithms for many settings. So can we reduce this problem to 1D? Because this looks like very closer to 1D. And our answer is for many of fairness notions and efficiency notions in this area, we can use some simple transformation which will do from 2D to 1D, and then you can use existing algorithms. But few things we cannot. And especially problem becomes in MMS, max min share. So alpha MMS may not exist in this. So we have come up with some different notion of approximation to MMS. But still, whether that is right or no, or what is a better fairness notion in this for approximate MMS is also an interesting problem. One should look at it. So our results are like, if you have EF1, you can use EF1 same here, EFX generalize. But proportionality and PropX do not generalize in 2D. So we have to little bit change the definition. Whereas alpha MMS do not exist in 2D. So like why proportionality faces this issue? See, on this allocation, if we talk about just what proportionality will say that 1/nth of Vi of M I should receive. So here Vi of M is 5 plus 6 is 11 for both the agents. So I should get 11/2. But no allocation will be ensuring 11/2 for both the agents. And like EF implies proportionality. So you can find out EF allocation here. But that allocation is not proportional. So proportionality definition typically is like 1/nth of what I can get whole bundle. So instead of that, you just do utility of all the other agents allocation and 1/nth of that. That we call proportionality with externality. And now EF in 2D domain will imply prop E. That one can prove very easily. So, efficiency like MNW, so Nash social welfare, now we cannot really worry because there are negative numbers here. So we don't, there is no natural extension to it in 2D. Like Lexmin algorithm, if we work with just utilities. And so that means if I get C1 only, then my utility is 1, -20, -30, -30 like that. So if you work with just utilities, Lexmin algorithm is known to give prop 1 and Pareto optimal. But on this instance, it will not give. Oh, this is after our transformation. Sorry, I will show it again. So that's instead of working with utility, what we observe that if we subtract this big number, this we call transformation now. So you have two numbers for each allocation. We get it into a real one number, WI. So now we have a new instance, which is a normal 1D valuation. And if you use this transformation, our results show that if allocation is EF in new domain, then is also EF here. And if it is EF here, it has to be EF here. It's both ways. For EF, EF1, EFX, prop E, prop 1E, prop X, and MMS, but not for alpha MMS, not for proportionality. And Pareto optimality and MUW also. Any of these properties, if they are equivalent in both the domains. So now we can adopt existing algorithms for 2D for this set of problems. Like if you work with utility and if you apply Lexmin, instead of utility, if you apply with the transformation, Lexmin will again give you prop 1e and PO. The challenge happens with MMS, max min share, because your max min share could be positive or negative. So we want to see that if we define that alpha MMS to be, if your max min share is positive, then it should be alpha times mu I. If it is negative, then it should be 1 by alpha times MMS. And we could show that it will not exist. Whereas for 1D valuations, there are already algorithms for finding out alpha MMS for goods as well as chores. So what we again proposed, we tried few more other definitions. There were again, which we were feeling natural extensions, like split your maximum share into two components, positive and negative component. And then based on that, you come up with, but that was not working quite good. We are not getting positive results. Even those alpha MMS were not existing. So we now call it shifted alpha MMS. So you shift your utilities by this some fraction 1 minus alpha times this, and for goods and alpha minus 1 by alpha power chores. And now we could show that the shifted alpha MMS exists in 2D valuation also. But is it the right notion? Or do we need to really think about what is approximate MMS? And these externalities which we have addressed is only 2D. But what if I don't get the object, but if whether Siddharth gets it or Umang gets it, that will have different valuations to me. It is called ND if there are n agents, based on who gets it. So Harris has one paper, I think this triple only, right? Which talks about ND valuations, ND externalities, which is more general. So they propose average share for generalization of proportionality, and we can prove that what we proposed and they are equivalent for ND, but for 2D, ours is better than their definition. But MMS, again, approximate versions, even they don't talk about it. So alpha MMS in general externalities, how do we come up with approximate version of MMS? That is interesting problem. One should look at it. Even MMS SX and increased complexity externalities between 2D and ND. And ND also not much is known. Very few results Harris has. So in summary, I think I'm on time. We looked into two problems. One where we try to learn neural network to get closer to EF1 allocations. And another problem we looked at externalities. How do you get fair and efficient allocation? And it will pose new challenges. Any questions? If no questions, I think we can go for a coffee.
So button ये वाला है. हाँ वही है. Try.
But sometimes I don't
एक स्लाइडर है कैसा?
ये कोई और टाइल एक्सपोज करने के लिए था उसको टाइप किया था
क्या हुआ? This one is very simple. It's working, it's working.
Okay. Hello. Welcome back. Let's all welcome Prajakta Nimborkar from CMI. She's going to talk about fairness in matching. So over to you, Prajakta.
Thanks. So, first of all, I thank the organizers for inviting here and for all of you to be here after a long series of talks. I will talk about matchings with fairness constraints. So here, unlike the other talks, the fairness would mean something completely different. I will first define the problem setup and then so here, this is a kind of matching problem as the title says. So we have a set of items and a set of platforms, and it's not a one-to-one matching as we usually mean. So the platforms can accept multiple items up to a certain capacity. So here the platforms have a capacity 2, which means each platform can accept up to 2 items. These are the upper bounds. So far, the standard matching, this is a standard matching problem and the algorithms, standard algorithms apply. But then the fairness constraints come into picture. And the fairness constraints say that the platforms don't treat all the items equally. So the items have various properties and the platforms want certain number of items having certain properties. So each platform can define its own classes on items. Here the platform P2 has defined 2 classes. One contains the items A2 and A3, and the classes also have their own quotas. So the platform P2 declares that it wants exactly one item between A2 and A3, and it can have, sorry, not exactly, up to one item between A2 and A3, and it also wants at most one item from A1 and A2. So as you see, the classes can overlap because A2 belongs to 2 classes here. No, sorry, everything is at most. Yes, so we are currently dealing only with upper bounds. We will come to a lower bound setting later, but I won't talk much about it. I'll state the result. Yes, no, items can go to one platform. Yes. As such, there is no harm in like even defining a many-to-many model on this. Just that we have defined this model for simplicity, but it exactly works the same way even for many-to-many setting. No, platforms can define their own classes. For example, here P2 has defined these classes, but P1 has not defined any classes, so which is perfectly fine. Any more questions about this model? So here the platform quotas can also be modeled as classes, because it can be the whole class on the neighborhood with whatever the capacity of the platform is. And our goal is to match maximum number of items to platforms. So the difficulty arises here because, for example, here A2 belongs to two classes defined by P2. So if we match A2 to P2, we can neither match A3 nor can we match A1. Right? So if we don't match wisely, we may not have a maximum matching, and still we get stuck up with a smaller matching, which we cannot improve. Yes, I will say that also. Yes. So these classes are called as fairness constraints or group fairness constraints, because each platform wants to be fair to each group, and hence it is not accepting too many items from any of the groups. So why do we consider this kind of model? And there are several real life examples which are captured by this. For example, if we want to select committees for various tasks, then from available pool of candidates, every committee wants expertise from all the required areas and doesn't want too many people from the same area. And of course, committees can have totally different goals. So it is natural that the requirements of every committee will also be different. So that justifies why every platform defines its own class. Similarly, if we are forming teams for projects, then again, the requirements of skill sets for every project are different, and each project can define its own classes from which it wants to pick team members. Yeah, so this kind of constraint, the group fairness constraints, have been previously studied for clustering and cuts and many other things. Yes, selecting speakers at a workshop, even accepting papers for conferences. You don't want too many from the same area. And yes. So a very simple case that I will describe first, where the classes are, they form a laminar family. What I mean by laminar is two classes don't have non-trivial intersection. Either they are completely disjoint or one is completely contained in the other. Again, these classes arise very naturally. For example, if you look at geographical boundaries, then countries are divided into states, which are divided into districts, and which are divided into cities and towns. And geographical boundaries perfectly form this kind of laminar structure. And a special case of this is partition, where the classes are disjoint. So only this case is there and not this one. So this maximum matching, when there are laminar classes, this just reduces to a max flow computation in a flow network. Really a very small exercise, I would say. So just like we reduce the bipartite matching problem to flows, here also we create one vertex for each item and one vertex for each platform. Additionally, we also create vertices for classes. And because of the laminar structure, the classes form a nice tree structure which can be put here between the items and platforms. So here we see that we have put vertices for classes. These vertices are not really required, but we have just kept them for nice look, so to say. Okay, and then we put all the edges, and for the quotas of classes, we put them as capacities on the outgoing edges, same as the platform quotas are put on the edges going out from the platform, and all the edges have capacity 1. Now here, if the items had more than one capacity, we would have put that here, and it would also have been captured by the same flow network. No. And we add a source and a sink, add all the edges, and then we compute a maximum flow in this flow network. And if you look at the item platform edges here, they give us a maximum matching. So for every maximum matching, there is a maximum flow, and vice versa. Through a max flow computation, we get a maximum matching here when the classes are laminar. Yeah. So the fairness constraints are given by these classes. So here P1 platform declares a fairness constraint that between A1 and A2 items, it will accept at most one. So actually these classes could be defined based on various properties that the items possess. Like as I said, maybe skill sets of people or expertise of doctors or whatever. Yeah. Okay, so as Siddharth pointed out, the general problem is very hard and there is a simple reduction from independent set problem. So we are given an independent set instance. We create vertices for all the items and we need only one platform. And we connect all these vertices, that is the item vertices to this platform, and every edge becomes a class and every edge has a quota 1 because the independent set problem requires that we pick at most one vertex or one endpoint of any edge. So this trivially becomes our group fairness, matching under group fairness problem. And even with one platform, it turns out to be as hard as the independent set problem. So every independent set corresponds to a matching which respects class quotas, and hence finding a maximum matching is as hard as finding an independent set. And there are no non-trivial approximations for the independent set problem. So we can't hope to solve this problem to any reasonable approximation. Matroidal constraints instead of laminar. Yes. So yeah, so so actually not, we didn't try Matroid as such, but then we have some generalization of it in the sense that instead of one laminar family, so first of all, the laminar family is separate for each platform. So different platforms can have their own laminar families. We also showed that if you look at the edges incident on one platform, if the classes form constantly many laminar families, then also we can get something like 1 over that constant many that much approximation. So we have looked at this partitioning of the class structure into multiple laminar families, and as long as that is constant, again we do have a reasonable approximation.
Besides the flow of
Yeah, that's just, I mean, it's just simple, straightforward. So B matching polytope won't.
Yeah, this is some polytope. Looking at the polytope structure.
So actually we didn't look at polytope structure because we won't get integrality because of the hardness. So yeah, but I think
say nice, nice. Maybe the question is the laminar polytope.
It would be integral because it's just a flow polytope. Yeah, I think we should look at matroidal constraints, which we have not looked at.
I think you can just write an NP and then write the decomposition over integral. So the bi-hierarchy is kind of a necessary and sufficient condition. If you're not bi-hierarchical, there are examples where you can't do these decompositions. I don't know if you have looked at it.
Yeah, we have referred to their work. Yes. We have also referred to a few more things, but usually the setup is a little different from what we are doing. So, I mean, I didn't list out them because there is some difference in the initial setup or the problem definition. But yes, there is a lot of related work as such. We have looked at this Budish et al. As well. Okay, so next we come to this a case where we have only constant number of classes, and again this case is quite true in real life in the sense that even if there are lots of applicants or lots of people, usually the areas of expertise are very few. So first of all, so our result here is to give a half approximation when there are constant number of classes and multiple platforms. But to get that, first of all, when there is only one platform, we get an exact algorithm by solving an integer linear program. So here the integer linear program, again, because there are multiple items and we are only looking at one platform, but still it cannot have one variable for every edge. So we have to define the variables a bit differently. So because there are delta many classes, each item can belong to a subset of them. So we can classify these items into 2 to the delta many types. And now each item can have exactly one type because the collection of classes which contain each item that will define its own type. So the items have at most 2 to the delta many types, and we create one variable for every type. So this variable xi denotes how many items of a particular type I get matched to this single platform. So this is the integer linear program where we want to maximize the number of items matched, and xi denotes the number of items of type I which get matched to this single platform. And we have these quota constraints for each class. So whichever type contains the class C, sum over those variables should not exceed the quota of that class. And then we have a limit on how many number of items of each type we have. So that should, our xi should not be more than that. So this is an integer linear program which has 2 to the delta many variables and 2 to the delta many, order of 2 to the delta many constants. So it becomes a constant size integer linear program and can be solved exactly. Yeah, but for, because, we can use a dynamic program. It's almost like we can do brute force on, because this becomes a constant sized instance. So next, we show that if we have an alpha approximation for one platform, in our case, what I just showed, alpha is 1. This one is for multiple platforms. So we show that if we have alpha approximation for one platform, then we get alpha over 1 plus alpha approximation for multiple platforms. So because we have alpha equal to 1, we will get half approximation for multiple platforms. But this result is more general in the sense that even for non-constant number of classes, if we get some approximation for one platform, then it also translates to some approximation for this kind of approximation for multiple platforms. So the algorithm is really greedy. So it takes one platform, executes that ILP algorithm, which is the exact algorithm, and finds items to be matched to that one platform. And just removes those items and that platform from the system. So next it will take another platform and do the same, and so on and so forth. So we just treat platforms as, we just take one platform at a time and pretend that we are in the one platform case and keep matching items optimally from whatever is remaining. And now, how do we get our approximation? So let's look at the optimal solution. So suppose P1 to Pn are our platforms, and these are the ovals denote the optimal solution. I mean, the ovals denote the items which get matched to each platform in the optimal solution. So these are the items which get matched to the first platform, P1, and these are the items which get matched to P2, and so on. Now the question is, how will our algorithm do on these? So let's say this is the solution that our algorithm gives. So A denotes the solution of our algorithm and opt is the optimal one. So say our algorithm matches items in these vertical ovals to each platform. Now, when our algorithm matched items to P1, all the items were available to it. The last oval denotes the unmatched items. And note that we don't quite care for unmatched items left by the optimal solution. So we only look at what happens to those items which get matched in the optimal solution. Okay, so when our algorithm was matching items to platform P1, everything was available to it because we had not matched anything yet. Whereas when our algorithm matched items to P2, it did not have everything available from this opt of P2. It did not have in particular these three items available. So we will color items depending on what was available and what was not. So this is the coloring. So because these items were not available from opt of P2 when we calculated A of P2, so these are colored red, and everything else was available, so that is colored green. So this is the way we have colored each oval. Any question about this? Now, the number of items matched by optimal solution is, of course, all the items present here, which is the number of red items plus number of green items. Whereas our algorithm matches, of course, it matches red items, although to wrong platforms, but still it matches them. So our solution is certainly more than the number of red items. Also, because these green items were the available items, it also gets alpha approximation on them because of the one platform guarantee. So we get these two inequalities for our solution, and they are the ones which totally give us this alpha over 1 plus alpha approximation for multiple platforms. So is there any question about this? It's fairly a simple algorithm and analysis. Yes. And that is the added advantage in the sense that it also works in online settings when platforms arrive one by one. So another case. Weights on the edges. I think a similar argument will hold because the ILP can itself accommodate weights, and we can find a maximum weight matching for the ILP. So whatever we don't match will certainly have a lower weight than whatever we match. Yeah. Yes, the alpha approximation for one platform translates to alpha over 1 plus alpha for multiple platforms. It is independent of number of classes. So our half ratio comes because we have constant number of classes. There is another very simple case. So the number of classes is not constant, but each item is present in at most delta many classes, say constant number of classes. Then again, we get a 1 over delta plus 1 approximation. And this is again a very simple greedy algorithm where we just take a platform and match items to it and continue this way. So this is a maximal matching like argument where if we wrongly match an item to a platform, it can at most block delta other items from getting matched to that platform. So just like we show that a maximal matching is a half approximation to maximum matching, this also gives a 1 over delta plus 1 approximation. So although this result is very simple, there are some interesting connections with hypergraph independent sets. Per platform, yeah. Each item is in at most delta many classes of any platform. So this has some connections with hypergraph independent sets. So a hypergraph is a collection. I mean, this is a graph where each edge is a set of k vertices, and in a normal graph we have k equal to 2. So it's a generalization of graphs. And let's say the maximum degree is delta. So each vertex appears in at most delta many edges. And there are two ways in which independent set is defined for hypergraphs. One is a strong independent set where we pick at most one vertex from each hyperedge, and there is a 1 over delta approximation known for this. One can also say that one can also look for a weak independent set where we don't pick the entire edge, but we pick at most, all but one vertices from each hyperedge. So both of these notions coincide when we have graphs, because picking at most one vertex is same as not picking all vertices for an edge. But then there are better approximations known for weak independent set. So our result actually implies a generalized independent set result for hypergraphs. So here, instead of saying that we will pick at most one or at most all but one vertices from each hyperedge, we can just define some quota for a hyperedge, and we want to pick QE vertices from each hyperedge. So the reduction goes like this, that each class becomes a hyperedge, and the quota of that class becomes the quota of that edge. And then picking items actually means picking vertices from this hyperedge. So we get the same 1 over delta plus 1 approximation for a generalization of these two notions. Now I come to a different notion, which is again used at many places in literature. So this is called proportional fairness. And why do we consider this notion? So first of all, when we execute a procedure like many times, for example, when we are admitting students to colleges, so there defining quotas as specific numbers is not very nice, because the number of items might change. That is, for example, the number of students who apply to a particular college or number of students from a particular category who apply to a particular college might be different over different years. So we don't have these fixed quotas on classes, but we put proportional bounds. So we say that if there are MP many items matched to a platform, then for a class C, at least an alpha fraction of them and at most a beta fraction of them should be from class C. And the alpha and beta are fractions, so they are between 0 and 1. And along with that, we also have upper and lower bounds on this MP, which are like absolute bounds. And here we want to maximize the number of items which are matched to satisfied platforms. Satisfied meaning the platforms whose all these constraints are met. So this was studied previously in this paper, and they show NP hardness for even one platform when the classes are arbitrary. And they give a randomized approximation where there is some violation of constraints. The approximation factor is a little complicated. That is, it is 1 plus epsilon, but the epsilon has a certain bound. It doesn't work for all epsilon. So we look at this case when there are multiple platforms, but only disjoint classes. So we look at this case when there are n platforms and the classes are disjoint, and we give an order L approximation where L is the maximum lower bound for any class. So among all lower bounds, this L is the maximum one. So we have order L approximation. The algorithm works in order n square time, but then there is a slight violation of constraints, which is multiplicative violation. So instead of alpha fraction coming from a class, we might have alpha minus, to be precise, 3 over L fraction coming from a class. And similarly, instead of beta, it might be beta plus 3 over L fraction. So this is the slight violation of constraint that we get. And actually there is a somewhat matching hardness result, and that is L over log L hardness of approximation, even when there are no classes. So you just have a platform and you want to satisfy the upper and lower bounds of the platform, and that would still have this hardness result. So actually here, if we don't want this violation of constraints, then we get only an order U approximation where U is the maximum upper bound. But then, and that algorithm is simple in the sense that we again match items greedily to each platform. And this greedy solution itself turns out to be order U approximation. But then, of course, the upper bounds can be very large in practice and may not, they may not be practically very appealing. So this one, yeah, so this is a better approximation with some price in terms of the violation constraint. Yeah, so actually, yeah, then only there are upper and, yes. So actually this hardness comes from, again, matchings in hypergraphs. So like you create a hypergraph out of this by creating one vertex for each item and platform, and each hyper edge defines a feasible solution for a particular platform. So then because hypergraph matching has this kind of hardness, our matching actually corresponds to picking a maximum size matching in a hypergraph. So even without classes, just to meet the upper and lower bounds, we get this L over log L hardness, where L is the size of each hyper edge.
I have a bipartite graph. In the case of no classes, every vertex on every platform has to be matched to at least some L, and it moves to some U.
Yes.
Then some lower bound, upper bound. And the claim is that process is order L log L over log and algebra.
Yes.
Yeah.
Actually, flow so the problem with using flows with lower bounds is that if the instance is not feasible, that is, you can't satisfy all platforms, you won't get a solution by flows. So yes, but if it is not feasible, then the flow algorithm will just tell that it is infeasible. But then if all platforms cannot be satisfied, then we want to satisfy as many platforms as possible. So if all the platforms can be satisfied, very well, flows with lower and upper bounds will give us a solution. Yeah. Yeah.
Demand also, of course it won't go.
Yeah, because it won't be met. So in fact, if we just consider lower bounds, again, the same thing happens. That is, If we can't satisfy all lower bounds, then flows don't give us anything. Yeah. Yes. Yeah, we have not thought about like perturbing the constraints. Sure, that is one thing. Hmm.
If this is scalar, multiply all of the platform bounds by some scalar. Figure the lowest allowed at which all are satisfied given it's a like flow or
A flow.
what is the smallest L such that all vertices are satisfied? That like, so if the L is the same across all, that is
Yes.
first time. The constraint matrix is the objective is to whatever reason. The maximum
So yeah, in general, because the neighborhood of each platform may not be the same, we won't be able to use the same L. So yeah, I don't know like how we would do a binary search.
Same L across all.
Yeah, then we should be able to try out various Ls. Yes.
Is the same across all.
No, actually, each class has its own alpha and beta. The classes are them. It is platform dependent and also the class dependent. So it will be alpha ij actually for platform I and class j. And yeah, again, that is required because we may not have enough items coming from a particular class to say that this should be satisfied. So yeah, I think it will be nice to determine some perturbation which actually works, but we have not really addressed. Yeah. So yeah, this is essentially all. There are some more results in the paper, but then they are not very nice and simple to state. So. I mean, yeah, it's like this approximation with this violation and that. Never. So yeah, what we could really not do is extending this proportional fairness to non-disjoint classes, which we would have been happy to do. We could not even get anything for laminar classes for that matter. Only for disjoint classes we get this. And then one criticism that we also received is that we don't incorporate item and platform preferences. So there is some work that we have done in this regard, at least to incorporate item and platform preferences. But then, yeah, we have to use a linear program and round it and so on. But that is not part of this series of work. So yeah, that is all about it. And thank you for attention. Yeah, for constant number of classes, it is hard. I think it comes from SAT. The reduction is from SAT to SAT. Yeah, the independent set hardness was for general. But yeah, that is a different reduction. No, we don't know hardness of approximation. Yeah. So they are called fairness constraints because it is seen as like the items have different properties. So like we all are familiar with our admission system where we have different quotas and well, okay, they are said to be fairness constraints. So as such, it also comes from literature, because for clustering and cuts, it is all called as pair clustering, pair cuts. So we have borrowed the name from there. But yeah, the notion of fairness is in the sense that no group of items is overrepresented. Diversity, yes. In fact, we also use the term diversity constraints, but only for the case when there are only lower bounds and no upper bounds. Yeah. Yeah. Hmm. Yes. So having no classes is like having one entire class defined on the neighborhood. So there are platform quotas. Yeah. Yeah. So platform quotas we can represent as one whole class on the neighborhood, and the quota of that class is the platform quota. So that one class is always present, and that will give us half approximation. Okay. So thank you again.
Thank you.
The simple results that you saw, we were getting confused with that. No, but in the nice thing, there are three different people.
Yes, actually, almost the same time, but then I 20 minutes. I finish in 40 minutes.
Yeah.
I'm usually known. I don't know.
That's a good thing. It's better than looking at the watching.
Sure.
Let's welcome Vishnu Narayan from Tel Aviv. He'll be talking about fair division via quantile shares.
Thank you. I want to start by, can you hear me? Should I? Yeah, I wanted to thank the organizers, Siddharth, Umang, Sujit, and everyone else that was involved for organizing this and inviting me. It's been great so far. I'm going to talk about something slightly different from the other talks. This is titled Fair Division via Quantile Shares. So I'm going to be talking mainly about a new fair share notion that we define. So this talk is not going to be much about envy, but about shares. I'm going to define this, motivate it, and then analyze it. So this is joint work with my postdoc advisor at Tel Aviv, Michal Feldman, and with Yakov Bavichenko and Ron Holzman from Technion. So I'm sure we're all familiar with this stuff, but I'll give you like a 2-page introduction, fair division for completeness. So, the problem that you want to solve, of course, in general is fair deterministic allocation of indivisible items. So we have how should you divide a set M of M items? In our talk is mostly going to be about goods, but we'll get to chores later for a bit, amongst a set of N agents. We have some items and we want to give them to the agents. And agent I has a valuation function P sub I, which is normalized. That means VI of the empty set is 0 and monotone. These are two extremely standard assumptions that are made in pretty much 100% of fair division work, and that's going to be important in a minute. So note that we want an allocation that is indivisible, so we're not going to consider fractional allocations, and deterministic. And the questions that are typically asked is, in the fair division literature, is there an allocation that's fair? Can we efficiently compute such an allocation? And before we can answer these, of course, you have to know what a fair allocation is. As you probably know by now, there are broadly 2 categories of fairness. That's envy-based and share-based fairness. So in the envy-based fairness, an allocation is envy-free if no one envies anyone else. But NV-free allocations, of course, don't exist for indivisible items. So we define some relaxations like EF1 and EFX. A is EF1 if whenever I envies J, there exists some item G in AJ, such if J hides G, I no longer envies J. Importantly, EF1 allocations are known to exist for all profiles of monotone valuations. So the whole class that is monotone valuations that is always considered in fair division. And this is via the famous NV cycles procedure. And for EFX, the NV is eliminated by hiding any item. So this is a stronger condition. But of course, we don't know whether this exists. It's a major open problem, but there's no counterexample even for monotone valuations. So as far as we know, the EFX also might exist for monotone valuations. So what about fair shares? We haven't had much talk about fair shares so far in this workshop. So you guys know the standard fair share notions like proportionality and maximum share. In general, a share function is a function tau that assigns a share value to every agent, which depends on the valuation function of the agent and the number of agents. And an allocation is fair if every agent receives a value that is at least its share. So Vi of AI is at least tau of Vi, n for all agents I. Some examples include the proportional share, where the share value is 1 over n times the value of the grand bundle, and the maximum share, where it's that max and min thing. So it's the maximum over all allocations of the minimum value of a bundle in that allocation. So this talk, we're going to focus on fair shares. So to recap, with fair shares, there are m items that are to be allocated to n agents. Agent I has a monotone valuation, and given a class C of valuations, tau from, sorry, that should be C. C cross n to R is a share. And for an n agent allocation problem, in a fair allocation, every agent gets at least tau VIN. Note that the share does not depend on any Vj for j not equal to I. And also, fairness does not, unlike in the case of NV, fairness does not depend on the bundle that the other agents receive. So an agent is going to be fair if it receives a bundle that is at least its fair share. And it doesn't care about what the other agents receive. So what sorts of questions are typically studied in the case of fair shares? Unanimously, the most common one is feasibility. So a share is feasible for some class of valuations C if for every profile of valuations in that class, there exists some allocation such that every agent meets its fair share. So Vi of AI is at least tau of Vi, n for every I and n. And this is for all profiles in C. So the main questions we want to study with fair shares is for given a fair share notion, for what classes is it feasible, or constant approximations of it feasible, and so on. We're going to call a class tau, a share notion tau, universally feasible if it is feasible for all monotone valuations, V. So let's look at the feasibility of some famous shares. We'll start with the maximum-based shares. So the maximum share was first defined by Budish in 2011. And here the agent partitions the items into n bundles, and then an adversary picks a bundle. So picks the lowest valued bundle for the agent, and that gives you the value of the share. So Budish left open the problem of whether the maximum share is actually feasible. But it was solved pretty soon in this paper by Prakash and Wang from 2014. And it turns out that, somewhat surprisingly, the maximum share is infeasible even for additive valuations. So there are instances for which there is no single allocation that can give every agent a value at least its maximum share. So then the fair division community moved on to constant fractions of the maximum share, and we got some positive results. So 3 over 4 fractions of maximum share is feasible for additive valuations. And in fact, it's now some constant slightly higher than 3 over 4, thanks to Jugal and Hanane. And for other classes like submodular and XOS, there are again constant fractions that are feasible. And there are over a dozen papers on, probably around 2 dozen papers now, on constant fractions of the MMS. But no constant fraction of the MMS is feasible for general monotone valuations. And this is extremely easy to see. If you have, for example, 4 items A, B, C, D, and agent 1 has a valuation where it has positive value for sets A, B, and C, D. Sorry, and agent 2 has positive value for sets A, C, and B, D. Then there is no allocation that gives both agents positive value. So this is the maximum partition for agent 1, where it gets positive value. So the MMS is positive for both agents. This is the maximum partition for agent 2. but no single partition can give both of them positive values. So the MMS is infeasible for general monotone valuations. So what about the proportional share? Again, here it's even easier to see that no fraction of the proportional share is feasible. You have two agents and a single positively valued item, and you can't get any fraction of your value. So there have been many other similar notions of share, like the any price share, prop one, which is not exactly a share, but almost a share, and several others that aren't as popular. And what's common for all of these is that they're all studied for the class of monotone valuations, but none of them and no constant fraction of them is feasible for monotone valuations, which is sort of weird, especially when you compare it to EF1 and to NV. EF1 is feasible for monotone valuations. It's possible that even EFX might be, but there's no known non-trivial share notion here. So that you can see where this is going raises the obvious question: is there a reasonable notion of a share that is universally feasible? And that's one of the starting points of this work. We actually got here through a kind of circuitous route, but that's one of the questions that we're trying to answer now. And in order to do that, I'm going to define a new notion of a share called the quantile share. So I'll define it, motivate it, and then analyze it. So everything about quantile shares can be encapsulated with one very simple sentence, which is loads. Yeah. So consider an agent who believes that the allocation of the items will be done uniformly at random. So what does this mean? So imagine that you were to enumerate all of the n to the m allocations and then select one uniformly. This gives you a random bundle for every agent. Equivalently, you could go over all of the items independently and assign each item to one of the agents uniformly with probability 1 over n. So that's the simplest sort of random procedure that you can think about to assign items, right? But the idea behind quantile shares is to compare deterministic allocations with this simple random procedure. Use the random procedure as a benchmark for fairness. So we let xi be the random bundle of agent I in this uniformly random allocation, which is equivalent to giving each item with probability 1 over n independently. So the quantile share, we're interested in the quantiles of the distribution of vi of xi. So for every q in 0, 1, the q quantile share tau sub q is defined to be the q quantile of the random variable distributed as vi of xi. So what does this mean? If we were to look at all possible values that vi of xi could take across all allocations and the number of allocations in which it takes that value, the q quantile is the value for which a q fraction of these allocations is weakly smaller. In other words, agent I asks, what is the probability that my bundle in a uniformly random allocation is weakly worse than the bundle I actually receive in this allocation under consideration? And an allocation is q fair if this probability is at least q for all agents I. And of course, what we want to know is for what values of q is the q quantile share feasible? Is that clear? Are there any questions about this? Yeah, the probability that you're doing better than this. Yeah. Okay, feel free to stop me at any time.
Stands for other shares as well, but it's not obvious that you're certifying this is also not. You have to draw in a random sample. This is well defined, but I'm wondering, like, you have a bundle, you want to estimate whether it's two quantile or not. How do you just, it's easier to certify than say anything.
I haven't thought about certifying it, but you can
Well, let's say
estimate the quantile very, very quickly. Yeah. Yeah. Yeah, and that should give you, I haven't worked it out, but it should give you a very fast, accurate estimation. Okay. So for what values of q is the q quantile share feasible? These are our main results. We show that for q more than 1 over e, the q quantile share is infeasible, all classes of valuations. The main result, the most interesting result is it's not an unconditional result, but it provides strong evidence for the feasibility for the constant fraction. So for q at most 1 over 2e, which is also a constant fraction, the q quantile share is feasible for all monotone valuations if this very famous conjecture of Erdős is true, if the rainbow Erdős matching conjecture is true. And we'll get to explain the conjecture in a minute. We also show some unconditional results for subclasses of valuations. So for example, for additive valuations, again, a constant. For Q at most 0.14 over E, the Q quantile share is feasible. And we solved the problem completely for unit demand and matroid rank valuations. So for Q equal to 1 over E is the exact critical value for feasibility. Yeah, yeah, we'll get to that near the end of the talk.
Just to interpret the result, but saying it's like, let's look at the advantage. It's like you can all for all monotone valuations, there exists a partition such that the probability, like, if the agent were to do the shear calculation, any fraction of the random bundles would be below this.
Yes. Yeah. So every agent, there exists an allocation that makes every agent 1 over 2E fair. Yeah.
Right now, even for this unconditional result, the computational question is something we'll go to.
Yes. I can tell you pretty quickly that there's no construction here at all. These are all lead to polytime algorithms. So that's something that I'm leaving as an open problem, the computational question. Okay. So here's an alternate interpretation, which gives some more nice motivation for the share notion. Quantile shares as veto lists. So suppose an allocator who does not know the valuations tries to allocate according to the following procedure. The allocator first solicits veto lists for allocation. So every agent submits a veto list of allocations of size at most L for some L. And fairness here is captured by the fact that L is the same for all of the players. So all the players submit equal size veto lists. And then the allocator comes up with an allocation that does not appear in any of the veto lists. So this is an equivalent formulation. And the question we want to answer is how large can L be such that the allocator's task is always possible for all profiles? Yeah, not the number of bundles, the number of allocations. So we're looking at all of the n to the m allocations for the veto thing. So if the agents are vetoing allocations rather than bundles, it's exactly the same. No, it's equivalent. Yeah. Yeah, because giving each item independently with probability 1 over n is the same as enumerating all the allocations and picking one uniformly. Right.
L would be something like n to the m times q.
Exactly. In the absence of any assumptions, the answer seems trivial. If L is at least, sorry. No, they're vetoing the allocations in that interpretation.
Can you do with bundles?
It will be, yeah, I mean, you have to analyze the mass with which you get each bundle. It's kind of the same thing. Yeah, so you have to give, exactly, you have to give everyone the same mass of veto and, yeah.
Once you veto a bundle, every other, like, we distribute everything else is done.
Yeah. But you're vetoing allocations, but okay, we'll get to that in a second. That's on the next slide. Right, so in the absence of any assumptions, the answer seems trivial. If L is more than the number of allocations over n, this is impossible. If L is less than the number of allocations over n, this is possible, because if it's less than the number of allocations over n, even if they veto disjoint allocations, some allocation survives. But of course, that whole analysis is not considering the monotonicity of the agent's valuation functions. So a list L is monotone consistent if Si S minus I is an L implies for all Si prime that are, it should say strict subsets actually of Si prime S minus I is also an L. So if an agent vetoes an allocation in which it gets some bundle, it should necessarily veto all allocations in which it gets a strict subset of that bundle. So for all lists that are consistent with monotonicity, the question is now how large can L be such that the allocator's task is possible? So the reformulation of the main result is for all n tuples of monotone consistent veto lists of size L at most, now number of allocations over 2E, the allocator can find an allocation that is not in none of the veto lists, assuming the conjecture. And this is really cool, right? This is much larger. So there's actually a constant fraction of the allocations as soon as we add monotonicity, rather than the obvious 1 over n without monotonicity. So now let's start with the negative result. This is extremely easy to show, the infeasibility of the 1/e quantile. It's a very simple example. So consider the case where the number of items is equal to the number of agents minus 1, and all the items have strictly positive value. So in every allocation, there's someone that gets nothing. And the probability that xi gets nothing is 1 minus 1 over n to the n minus 1, which in the limit is the constant 1/e. So you can't do better than 1/e. As n grows larger, if you have n agents and n minus 1 items, in this random allocation, each agent is getting nothing with probability 1/e. So the Q quantile share is infeasible for Q more than 1 minus 1 over n to the n minus 1, which is approximately 1/e. Now, in the other direction, a simple way to get a positive bound is to show the feasibility of the 1 over n quantile. So if every agent eliminates allocations that are located strictly below the 1 over n quantile, of course, there's an allocation that survives. And so the 1 over n quantile is feasible. So those two simple results give us that for two agents, Q equal to 1/2 is the critical threshold, because 1 over n is 1/2, and 1 minus 1 over n to the n minus 1 is also 1/2. But of course, for n at least 3, we have a gap, which we saw earlier. So 1 over n is 1/3, and 1 minus 1 over n to the n minus 1 is 4 over 9. This thing vanishes, and this thing is a constant. Yeah, it holds for all classes. I mean, it doesn't. You only need to define the valuation for singletons, and yeah, it's just as long as it's positive for everything. Yeah, the MMS is 0. Yeah, we'll get to comparisons of the MMS near the end. It's also pretty interesting. So how do we get anything better than this as a bound, and 1 over n? We're going to use this conjecture of Erdős. So it's the Erdős matching conjecture. Given a K uniform hypergraph, so a family of K element sets F, the matching number nu F is the size of the largest matching, that is the largest collection of pairwise disjoint sets in the family F. So for this picture, for example, we have a bunch of elements. We have 5 sets that are all of size, all have 6 elements. What is the matching number for this example? It should be easy to tell visually. Sorry, I didn't. Yeah, it's 3. So you can tell that those 3 form a matching. So Erdős asks, how large can a K uniform hypergraph? By large, we mean the size of the family, the number of sets. How many sets can a family, which is K uniform, on M vertices, on a ground set of size M be, if it has no n matching? So this resulted in a now quite famous conjecture, the Erdős matching conjecture. For every mk and n, such that m is at least kn, and for every family that doesn't have an n matching, so the matching number is strictly less than n, we have that the size of the family is at most the max of some expression that I'll explain in a minute. So equivalently, if the family of sets is larger than this, then it necessarily has a matching of size n. So what are these expressions? It's very easy to see what this actually means. The first one corresponds to what I'm going to call hypergraph A. This is all, note that these are, I'm going to tell you what hypergraphs they are, and they are hypergraphs that don't have an n matching. So the first one is all K element sets containing at least one element of the first n minus 1 elements. So if every set contains one of the first n minus 1 elements, then you cannot find n sets that are pairwise disjoint. That's pretty simple. So that's m choose k minus m minus n plus 1 choose k. And the second one is all K element subsets of the first Kn minus 1 elements. Again, if you were to choose a matching of size n that is pairwise, I mean a matching of size n, it has to have Kn elements. So this is Kn minus 1 choose k, doesn't have such a matching. So the reformulation of Erdős matching conjecture is that for every mkn such that m is at least kn, either hypergraph A or hypergraph P is the extremal example. So there are no values of mkn for which you have another hypergraph with that is larger than either of these two. So this was apparently one of the favorite conjectures of Erdős, from what I've read. And there's been a huge amount of work on it in the last 50 years. Specifically, it's true for k equal to true. This was shown by Erdős and Galay. It's true for k equal to 3. This is a long series of works that was completed quite recently by Frankel, 2017. It's also true for n equal to 2. That is for pairwise intersecting families. You may have heard of the Erdős-Corrado theorem. And it's also true when m is sufficiently large relative to n and k. So this was first shown by Erdős, and then the bounds on m for what sufficiently large means have become weaker over time. And currently, they almost resolve the conjecture. In fact, if m is more than b of k comma n, which is 5/3 kn, for sufficiently in the limit, but for sufficiently large k and n, then the conjecture is true. And this is approaching the conjecture m at least kn already. And it's true for some other asymptotic cases where m is smaller than this value, but only for some small regions of mkn. So that brings us to the question of how do we connect the Erdős matching conjecture to quantile shares in order to analyze it. I'm going to start by the simple observation that the Q quantile share is feasible for all monotone valuations, if and only if it is feasible for all monotone 0-1 valuations, where the value of every set is either 0 or 1. So 0-1 valuations capture all of the hardness for quantile shares. So the forward implication is direct, of course. And for the other side, consider the Q quantile of a given monotone valuation, and we're going to construct a 0-1 value, a monotone 0-1 valuation. So it's just going to set everything to, the bundle that is here and everything to the right to value 1, and everything to the left to value 0. So of course, any Q fair allocation gives all agents a 1 bundle now. So the same allocation is Q fair for the original values. And so it suffices to consider monotone 0-1 valuations to find bounds on Q. We're going to do that for the rest of this talk. Are there any questions about this? Okay, good. So we'll start by analyzing the case of identical valuations. So here are the similarities between the Erdős matching conjecture and quantile shares. So the vertices are, of course, the items m that we want to assign. And the hypergraph is all of the 1 bundles. So the bundles of value 1. So this means if we have a matching now, a matching of size n in this hypergraph, we're giving everyone value 1, and we're good. If there's no n matching, then it's impossible to allocate the items so that everyone gets a 1 bundle. So then we can use the Erdős matching conjecture to get a bound. So it says that if there's no n matching, there's a upper bound on the number of 1 bundles, which is a lower bound on the number of 0 bundles. And so if there's a lower bound on the number of 0 bundles, when everyone has the same identical monotone valuation, then the Q quantile is at 0 and not at 1. So the allocation is Q fair, even if you give everyone the empty set. And that's it. So we'll get to the more detailed proof in a minute. I mean, a sketch of the more detailed proof. No. We need the rainbow version of the conjecture for the non-identical, which is almost exactly the same thing and the same proof. Yes. So those are the similarities, but of course, that leaves out the main difference, which is what is k in the quantile shares problem. The Erdős matching conjecture is for n, m, and k. And it turns out that here, a careful choice of k, where k is equal to floor of m over n minus 1, does the job. If you select m appropriately, k appropriately, then you can use the Erdős matching conjecture to get the constant bound that we wanted. So the theorem for identical valuations is that if the Erdős matching conjecture is true, the 1/2e quantile share is feasible for identical monotone valuations. So without loss of generality, we can assume that m is sufficiently large and that m over n is an integer. We can do this by adding dummy items that have value 0 to everyone. So these dummy items, they don't affect anyone's valuation for any bundle that they get. They also don't affect the quantiles, because if you give all of the items uniformly and then you give these extra items uniformly and they all have value 0, they're not doing anything. So let k equal to m over n minus 1 now for our appropriately chosen m. And suppose there is no n matching. So there's no allocation of 1 bundles. Then via the EMC, we can show that a fraction of at most 1 minus 1 over e of the k subsets are 1 bundles. This is the main part of the proof. It requires us to select m, k, etc. appropriately and show a reduction to that size. So a fraction of at least 1 over e of the k subsets are 0 bundles. Note that we're only considering allocations that give everyone exactly k items, because the Erdős matching conjecture is for partitions into bundles of exactly the same size. But by the Kruskal-Katona theorem, which we'll get to in the next slide, a fraction of at least 1 over E of the K prime subsets for any K prime smaller than K are also zero bundles. So the Kruskal-Katona theorem talks about the size of the shadow of a family. The shadow of a family of K element sets is the number of K prime element sets for K prime less than K that are subsets of these K element sets. Essentially, the theorem says that if there are a lot of K element sets in your family, then there are a lot of K prime element sets in its shadow. So in a random allocation, the size of xi is also less than m over n, which is the expected value. You have m items, n agents. On average, you're getting about m over n. So by the whatever central limit or whatever, the size of xi is at most m over n with probability approximately a half. So that 1 over e becomes conditional on this. Vi of xi is 0 with probability at least 1 over e. And so overall, you have that the probability of getting a zero bundle is at least 1 over 2e. That's the proof for identical valuations. That's a sketch of the proof. So
far, it is actually good for any sort of list of values.
sorry, I didn't understand the question.
Till the last line, till the last two lines.
Yeah.
The proof would have worked even if I had given any set of bundles without like where did the monotonicity kick?
The monotonicity it kicked into the fact that we're considering monotone 0-1 valuations. There are 0 bundles and 1 bundles, and this 0-1 valuation is monotone. And you can map any monotone valuation to monotone 0-1 valuation with the same value ordering over the bundles, and switching from 0 to 1 wherever you want to make the proof work.
So the 0-1 is like saying here's a large list of bundles.
Ah, right. So the shadow of if at least 1 over e if the K subsets are 0 bundles, by monotonicity, the shadow for any K prime less than K is also all 0 bundles. Yeah. That's the whole place that we use. Right. So this is about the Kruskal-Katona theorem. So the shadow of a collection of K element sets on K prime is all of the subsets of size K prime that are a subset of some set in the family of size K. And Kruskal-Katona gives you an exact answer for how small the shadow can be. Yeah, the size is at least if this size is x choose K, this size is x choose K prime. That's a sort of loose bound that this gives you, and that's all we need. So in our case, we know that the shadow consists of 0 bundles only, with is by monotonicity. Right. So now what about non-identical valuations? Here we have to use the rainbow version of the conjecture, which is also famous, also has a long list of work, and is also, in my opinion, getting close to being solved. So given n hypergraphs h1 to hn, a rainbow matching is a selection of vertex disjoint hyperedges, one from each hypergraph. So it's like selecting a bundle from each valuation function to assign. So the rainbow conjecture is the same. If an n tuple of hypergraphs has no rainbow matching, then at least one of these hypergraphs is bounded in size. So has at most the exact same expression of the number of hyperedges. Or equivalently, so there's a stronger conjecture than the Erdős matching conjecture, and it's also been proved for special cases, converging on the entire conjecture now. So if you can give all of the agents 1 bundles, you make that assignment and you're done. Otherwise, if there is no n matching, then at least one of the agent's valuations is such that the 1 over 2e quantile is at 0. And you can give that agent the empty bundle. So our main theorem for general valuations, if the rainbow Erdős matching conjecture is true, the 1 over 2e quantile share is feasible. So yeah, it's the same, essentially the same proof. So that brings us on to the yes, you cannot do better than, even though we conjecture that the actual answer is 1 over e, using the Erdős matching conjecture, you cannot do better than 1 over 2e. Yes, it would, and that's an extremely good question, because the combinatorics community does not try to prove it to a multiplicative factor, but that's something we can try to do to get a constant factor here. That's a great question. Yeah, that's one of the open problems as well. So for additive valuations, we can show unconditionally that the 0.14 over e quantile share is feasible. So it's very simple. The round robin algorithm achieves this goal. So the first step is to prove that the first agent to pick in round robin reaches the 0.14 quantile. And the second step adds the over E part. So prove that every other agent loses a factor of at most 1 over E. Suppose agent 1's valuations are A1, A2, and so on through AN. So we've sorted them from highest to lowest value. So it's easy to see that agent 1 gets at least this expression, 1 over n times the sum over all AJ. Right? Because it gets at least A1, then at least AN plus 1, at least A2n plus 1, and so on, which is at least 1 over n times the sum of the A's. But also 1 over n times the sum of the A's is the expected value of the random distribution. So if you have Bernoulli IIDs B1 through Bm, we want to bound on the probability that the sum over all j equal to 1 to m bj aj is at most this 1 over n, this expectation. And the existing literature gives us these bounds. So what is the probability that a sum of IID random variables is below its expectation? This is, we just use the deviations of sums inequalities work by Feige and a bunch of other people. Specifically, we borrow a fairly recent lemma by Ariely et al. And rephrased for our context, it just says that for all A1 through AN, this probability is at least 0.14 times 1 minus 1 over n. So it's approximately 0.14. So what about step 2? So agent 1 is now 0.14 satisfied, 0.14 fair. For the other agents, observe that after I minus 1 turns, agent I just acts like agent 1, but with one difference. A set of I minus 1 goods was taken away by the first I minus 1 agents. So the probability that agent 1 doesn't get any of these I minus 1 goods in the random allocation is again 1 minus 1 over n to the I minus 1, which is approximately 1 over E. And conditional on that event, we just repeat the arguments of step 1. So you get 0.14 over E unconditionally for additive valuations. And you also get polytime algorithm round robin. So we have a similar theorem for, sorry? Oh, this is very likely improvable. I don't think 0.14 is tight at all. It's hard to improve this deviations of some stuff. There's been quite a lot of work on it, but it's very unlikely to be tight. Yeah. I think this is also 1 over E actually. That's what we conjecture. Yeah. No. For the round robin also, I don't think this is tight, but round robin is probably not optimal, I guess. Right. So we also have unconditional proofs for unit demand and matroid rank. I'm not really going to go over them. Unit demand is very easy. So for unit demand valuations, we repeat the arguments from the additive case, but note that in step 1, agent 1 reaches its 1 quantile because the value of its highest valued item is equal to the value of the grand bundle for agent 1. So 1 over E is actually tight. More interestingly, 1 over E is also tight for matroid rank valuations. So it is known that the maximum share is feasible. This is by work from Siddharth and Paritosh fairly recently. And we just have to prove that the maximum share has a quantile of about 1 over E. So this takes some work, and I'm not going to go into the details, but it's a straightforward calculation. Right, so I'm going to give you some remarks now. So I'm going to compare the quantile shares with MMS first. So given a class of valuations C, the Q quantile share is feasible for n identical agents with identical valuations, if and only if the quantile of the maximum share with respect to C and N is always at least Q. Because any Q fair allocation witnesses the maximum share partition. And if the MMS is feasible, then it's also Q fair. So what about Q quantile shares and alpha maximum shares? It turns out that Q quantile shares are incomparable with alpha maximum shares. So for any values of Q and alpha between 0 and 1, there are instances where one is larger and instances where the other is larger. So Q quantile shares, even the epsilon quantile share can be higher than the 1 minus epsilon MMS. So this isn't just, I think that shows in some sense that this isn't just working for monotone valuations because it's weaker than the maximum share. It's just a better way to do share-based fairness for monotone valuations. It uses the right units to compute fairness for monotone valuations. Okay, and another remark for supermodular valuations, Chambers and Eshenique showed that for any monotone valuation, there's a supermodular valuation with the same bundle order. So just like monotone 0-1 valuations, supermodular valuations capture all of the hardness for monotone valuations. So if the Q quantile share is feasible for supermodular valuations, it's feasible for monotone valuations. Just wanted to put that in there. And what about chores? So the picture for chores is very simple and very different. So if you have a single good that is assigned, then only one out of the n agents can get that good in an instance with just one good. So for n minus 1 over n of the allocations, you're getting 0. So your quantile for where you get 1 is very high. But for chores, if a single chore is allocated, then the agent who receives this chore is only 1 over n fair. So 1 over n is again tight for chores. There's nothing else to say about chores. So I'll end with some open problems. The first thing is, of course, to show unconditional feasibility for monotone valuations. One way to do this is to prove the Erdős matching conjecture or the rainbow version. You'll become quite famous, win a few prizes. So it's a good idea if you want to try it. The other one is, this is quite interesting, and Umang already brought it up, prove that the Erdős matching conjecture bound is correct up to a constant factor for the regions for which it's not already been proven to be correct. I don't think anyone in the combinatorics community does these constant factor things the way we do, so that would be interesting and give us a bound, a constant bound for quantile shares unconditionally. Then you can also prove this for other special cases like submodular, subadditive, etc. So we tend to conjecture that the actual answer is 1 over e for all of the classes that we've seen so far. And in fact, slightly more strongly, it's 1 minus 1 over n to the n minus 1. And that one example is the worst case example. So for some classes of valuation, we've already proved it, like matroid rank and unit demand. Also for small values of n and m, it's possible to prove it analytically. We can go probably farther than this with more ugly case analysis, not super interesting. And for slightly larger small values of m and n, you can prove it by solving an IP. And that's the farthest my laptop would go. So, sorry? No, nothing else. Just the I did try some random simulations as well. Yeah. So that would potentially give you the search for random examples, but they gave me nothing. Yeah. So yeah. I mean, they didn't find any counterexamples, so that's evidence for the conjecture for larger values. Yeah. So also, as you guys already noticed, improving the 1 over 2e bound will require techniques beyond the Erdős matching conjecture. Because if you are giving people approximately equal size bundles, then 1 over 2e is tight. You can't do better than this. So you can think of the example where you have n minus 1 items of value 1, and you have a billion items of value some tiny epsilon. One of the agents is not going to get one of the n minus 1 items of value 1. And then if your bundles are all approximately equal sized, you'd get about m over n of the remaining items as well, right? So the probability that the random allocation for the agent that doesn't get the first high value item is less than m over n is about 1/2. So the value of getting none of the first n minus 1 items and getting approximately m over n of the remaining items, the quantile is at approximately 1 over 2e. So for equal size bundles, you cannot do better than this. Yes. Yes.
There is a balanced partition.
Yes.
Which achieves
There's a balanced partition which achieves the 1 over 2e if the Erdős matching conjecture is true. There's no balanced partition that does better. We believe that there's always a potentially very unbalanced partition that gives you 1 over e, but that's very hard to show. Yeah. In the example I gave you, it would be giving the first n minus 1 agents the high value items and giving all of the zeros to the last agent of the epsilons. And finally, of course, of slightly higher relevance for an algorithmic workshop, our arguments for monotone valuations are not constructive, only those for additive, unit demand, and matroid rank. So can you find any algorithms for these or for other classes like submodular, subadditive, or can you find any hardness results for finding Q-fair allocations? And that's the end of my talk. Thank you. Any questions?
like this case, like binary valuation is monotone but 0, 1. That is hard, like that. So even the non-rate like no, not binary, binary just binary. So like you like a whole bunch of it's monotone. The valuation is 0 for a whole bunch of that's also.
Yeah, that's exactly where, that's the instances to which we apply the Erdős matching conjecture. Oh, yeah, we didn't try to find algorithms. That's an interesting question. Yes.
Fine, I realize the counting problem reduces.
Yeah, we don't have any unconditional result even for that class, right? So the unconditional result, the conditional result for Erdős matching conjecture applies to that class and therefore to all valuations. So we don't have any unconditional results.
So for some agents, the quantile value is 0, for some it is 1. Find the partition of the so that I'm wondering whether that seems like a hard problem.
Yeah, so an algorithm that gives that for a constant value of q also gives an unconditional proof for general monotone. Very wise.
So, okay, I'm giving you a valuation function and the value oracle. So give it a subset, it will return 0 or 1. And I guarantee it's a monotone value.
Okay.
Now, for some agents, you can also tell you being generous. If for these agents, the quantile value is 0, I don't care. For these agents, quantile value is positive. So find me a partition where all of them get positive, which is actually find a partition which is
Yeah.
This seems like a
Yeah. This is very recent work that we did in the last couple of months. We've not looked into the complexity of any of this at all, just the existence results. Yeah, that does seem hard though, I guess. Yeah. Yeah. Yeah, I mean, it's easy to see even for additive. If you have identical items of value 1, and you have, as m goes to infinity, the q quantile is at m over n for all values of q, but the alpha MMS is at alpha times m over n. Yeah. I mean, by the central limit, the q quantile is at m over n. Yeah. Okay, that's it. Thank you. Yeah. Sorry. Yeah.
So this seems like a ordinal notion, right?
Yeah.
What about it? Like 1 out of.
to define.
Haven't thought about it.
Random n partition, keep it random n plus like on Cn, like n plus some, n plus 2 n plus 1 or n plus.
Yeah.
Increase the instead of managing them like 40 people or 2n.
Yeah, I haven't thought about it, but I think that the proof would still work if you adjust the values of m and k appropriately. I think. Yeah. No, I don't know. That's interesting. I will think about that.
You can show that like maybe this is better or in comparison.
Yeah.
Seems like maybe the right thing to compare.
Okay.
I need to think.
Yeah, me too. Okay, if there are any other questions? Yeah. Yeah, but nothing for monotone valuations. We don't have any results other than the conditional result of the Erdős matching conjecture. For identical valuations for the original Erdős matching conjecture and for non-identical for the rainbow version of the conjecture. Oh, I didn't think about identical additive. That it might be easy. Yeah. Yeah. Yeah, identical additive might be easier. That's a good question. I'll think about that. Okay.
There's one, as soon as you have n more than n, only 1 over n probability that will miss the average.
Oh.
At least proportion.
Yeah. Okay, thank you. Organizing.
so I would like to show you